Space is full of secrets, but there's one mystery that stands out because it affects galaxies on an enormous scale: starbursts. These regions of rapid and intense star formation might not sound all that remarkable at first, but they play a massive role in shaping the evolution of galaxies, including their structure, movement, and even the chemistry of the universe. Why do some galaxies suddenly ignite with furious star production? And how does this process shape their future? To unravel this, we'll need to explore the wild world of starbursts and uncover why they matter so much in the story of galactic evolution. Now imagine this: deep in the vastness of space, certain regions are brimming with chaos. Huge clouds of gas and dust collapse under their own gravity, igniting into countless new stars at an astonishing rate. These aren't your regular star-forming regions, they're galactic fireworks, producing stars hundreds of times faster than normal. These starbursts don't just change the galaxies they happen in, they send shockwaves through space itself. But how? What triggers them? And what does this mean for the universe as a whole? Let's dive into these questions because the answers may just reshape how you see the cosmos. Starbursts aren't random. They happen when galaxies collide, when tidal forces rip through massive gas reservoirs, or even when a single galaxy's core is stirred up by gravitational forces. These triggers set off a chain reaction, compressing gas into dense pockets that ignite into stars. It's like pouring gasoline on a fire. Everything accelerates. What makes it so fascinating is that the amount of star formation in these regions can rival the activity of an entire galaxy. Think about that for a moment. A single starburst region might outshine billions of stars in a more stable part of space. But it doesn't stop there. Starbursts are messy. They're chaotic. The energy released by so many new stars being born creates intense feedback, like stellar winds and supernova explosions. These forces push gas and dust outward, sometimes even blowing material completely out of the galaxy. Scientists call this process galactic winds, and it's one of the reasons starbursts are so crucial. They don't just create stars, they also strip galaxies of the very material needed to make future stars. It's like a double-edged sword. A starburst can breathe life into a galaxy while simultaneously setting the stage for its eventual decline. You might be wondering, why does any of this matter? How can a single event, no matter how dramatic, affect the fate of an entire galaxy? The truth is, starbursts don't just shape individual galaxies, they influence the entire cosmic ecosystem. The material expelled by galactic winds doesn't just disappear. It enriches the intergalactic medium, the vast space between galaxies, with heavy elements like carbon, oxygen, and iron. These elements are essential for forming planets, life, and everything we see around us. In other words, starbursts help seed the universe with the building blocks of existence. Now let's talk about scale. Starbursts are most commonly found in galaxies known as starburst galaxies. These galaxies are relatively rare, making up only a small percentage of all galaxies, but their impact is anything but small. Some of the most famous examples include galaxies like M82 and the Antennae galaxies, where colliding galaxies trigger massive waves of star formation. These systems offer a glimpse into just how powerful starbursts can be. They churn out stars at rates that are dozens or even hundreds of times faster than normal, creating environments so bright they can be seen across vast cosmic distances. But here's the twist: starbursts don't last forever. They burn through their fuel quickly, often in just tens of millions of years, a blink of an eye in cosmic terms. Once the gas is depleted, the galaxy settles down, and its star formation rate returns to normal. However, the effects of the starburst linger. The newly formed stars go on to live their lives, some ending in dramatic supernovae that spread heavy elements far and wide. Meanwhile, the galactic winds continue to reshape the galaxy's structure, pushing material into new regions or out into intergalactic space. One of the most intriguing aspects of starbursts is their role in galactic evolution. Over billions of years, galaxies undergo dramatic transformations. Some grow into massive ellipticals, while others remain as sprawling spirals or irregular shapes. Starbursts often mark turning points in this process. For example, a galaxy undergoing a starburst might eventually merge with another galaxy, forming an entirely new structure. Or it might exhaust its gas and transition into a quieter phase of its life. These events aren't just milestones in a galaxy's story, they're pivotal chapters that determine its future. And then there's the question of how starbursts fit into the broader narrative of cosmic evolution. The early universe was a very different place, denser, hotter, and more chaotic. During this time, starbursts were far more common, as galaxies frequently collided and interacted in the crowded conditions of the young cosmos. These ancient starbursts played a critical role in shaping the chemical makeup of the universe, creating the first heavy elements that would eventually form planets and life. Without them, the universe as we know it simply wouldn't exist. But even in today's universe, starbursts remain vital. They offer clues about how galaxies evolve, how stars form, and how matter is distributed across space. They're also a window into the past, helping astronomers piece together the history of the cosmos. By studying starbursts in nearby galaxies, scientists can better understand the processes that shaped the early universe. It's like looking at a time machine, revealing the mechanisms that have driven billions of years of cosmic change. Starbursts don't just offer insight into the past, they also challenge our understanding of the present. Astronomers have observed that these events often occur in galaxies with highly unusual properties. For instance, some starburst galaxies are exceptionally dusty, with thick clouds of gas and dust obscuring their centers. These dusty regions act as nurseries for new stars, but they also make it difficult to study what's happening inside. Infrared telescopes, like the James Webb Space Telescope, have revolutionized our ability to peer through these veils, revealing intricate details about star formation processes and the movement of material within galaxies. Interestingly, starbursts are also tied to the mysterious activity of supermassive black holes. At the core of most galaxies lies a black hole millions or even billions of times the mass of the Sun. In some cases, the same gravitational forces that trigger starbursts also funnel gas toward the black hole, igniting what's known as an active galactic nucleus, AGN. These AGNs emit enormous amounts of energy, sometimes outshining the entire galaxy. The interplay between starbursts and AGNs is a hot topic in astrophysics because it reveals a delicate balance. While starbursts create stars, AGNs can suppress star formation by heating or expelling the surrounding gas. This relationship between starbursts and black holes raises even bigger questions about galactic evolution. For example, how do galaxies maintain this balance? Why don't all starbursts lead to runaway black hole growth, or vice versa? One theory is that feedback mechanisms play a crucial role. As the black hole grows and emits energy, it creates powerful jets and winds that regulate the flow of gas, preventing the galaxy from collapsing entirely into chaos. At the same time, the starburst itself generates supernovae and stellar winds that further shape the galaxy's structure. It's a cosmic tug-of-war, with each process influencing the other in complex ways. The chemical enrichment caused by starbursts is another critical piece of the puzzle. When massive stars explode as supernovae, they release heavy elements like carbon, nitrogen, oxygen, and iron into their surroundings. These elements are crucial for forming planets, atmospheres, and even life itself. In fact, the iron in your blood and the calcium in your bones were likely forged in the heart of a starburst billions of years ago. This connection between starbursts and the fundamental building blocks of life underscores just how deeply these events are intertwined with the fabric of the universe. One of the most fascinating aspects of this chemical enrichment is its far-reaching impact. Galactic winds driven by starbursts can carry these heavy elements beyond the galaxy, dispersing them into intergalactic space. Over time, this process contributes to the overall chemical evolution of the universe, enriching even the most remote corners of space. Scientists have observed this phenomenon in detail by studying the spectra of distant quasars, which reveal the presence of elements like carbon and oxygen in the intergalactic medium. These observations provide a direct link between starbursts and the chemical makeup of the cosmos. The study of starbursts also has practical implications for understanding the history of the universe. By observing galaxies at different stages of their lives, astronomers can piece together a timeline of cosmic evolution. Starbursts serve as markers in this timeline, highlighting periods of intense activity and transformation. For example, surveys of distant galaxies have shown that starbursts were far more common in the early universe, peaking about 10 billion years ago during a period known as cosmic noon. This era marked a time when galaxies were forming stars at an extraordinary rate, fueled by abundant gas and frequent interactions. But why did the frequency of starbursts decline over time? One reason is that the universe itself expanded, spreading galaxies farther apart, and reducing the likelihood of collisions. Another factor is that many galaxies simply ran out of the cold gas needed to sustain such intense star formation. As the supply of gas dwindled, star formation rates slowed, and galaxies entered quieter phases of their evolution. This transition is a key part of the story of how the universe went from a chaotic, starburst-dominated environment to the more stable cosmos we see today. Despite their rarity in the modern universe, starbursts remain an active area of research because they offer a glimpse into the extreme conditions that shaped galaxies billions of years ago. Advanced telescopes and simulations have allowed scientists to recreate these conditions in unprecedented detail, shedding light on the physical processes driving starbursts. For example, researchers have used computer models to simulate the collision of two galaxies, revealing how gravitational forces compress gas clouds and ignite rapid star formation. These models help explain the observed properties of starburst galaxies and provide valuable insights into the dynamics of galactic interactions. One surprising discovery is the role of magnetic fields in starbursts. While magnetic fields are often overlooked in discussions of galaxy evolution, recent studies have shown that they can play a significant role in shaping starburst regions. Magnetic fields influence the movement of gas, helping to regulate the flow of material into star-forming regions. They also interact with cosmic rays, high-energy particles that can heat and ionize gas, further affecting star formation rates. Understanding these interactions is an important step toward building a more complete picture of how starbursts work. Another exciting area of research is the connection between starbursts and cosmic star clusters. Starbursts often produce massive star clusters containing thousands, or even millions of stars packed into tight regions. These clusters are thought to be the precursors to globular clusters, which are among the oldest and most enigmatic structures in the universe. By studying the properties of starburst-driven clusters, astronomers hope to uncover clues about the origins of globular clusters and their role in galactic evolution. These massive star clusters, born from the chaos of starbursts, serve as living fossils of galactic history. They can survive for billions of years, long after the starburst that created them has faded. By analyzing their chemical composition and stellar populations, scientists can reconstruct the conditions in which they formed. For example, the presence of certain heavy elements in these clusters reveals the extent of chemical enrichment during the starburst phase. This data acts like a time capsule, allowing astronomers to peer back into the galaxy's past and uncover the events that shaped its evolution. One of the most intriguing findings in this area is that not all star clusters remain bound together over time. While some form long-lived globular clusters, others dissolve into their parent galaxy, spreading stars across vast distances. These dispersed stars, known as stellar streams, are another clue left behind by starbursts. By mapping these streams, astronomers can trace the remnants of past starburst activity and even uncover the history of galaxy mergers. It's a testament to the far-reaching influence of starbursts that their effects can still be seen billions of years later. Speaking of mergers, let's delve deeper into the connection between galactic collisions and starbursts. When galaxies collide, their gravitational forces disrupt the delicate balance of gas and stars, triggering widespread turbulence. This turbulence compresses gas clouds, setting off waves of star formation that can sweep across the entire galaxy. The result is often a spectacular display of activity, with starburst regions lighting up like beacons in the night sky. These mergers are some of the most visually stunning events in the universe, but they're also scientifically invaluable, offering a natural laboratory for studying the physics of star formation. Interestingly, not all galaxy mergers result in starbursts. The outcome depends on a variety of factors, including the galaxy's gas content, their relative velocities, and the angle of their collision. For example, Gas-rich galaxies are far more likely to experience intense starbursts during a merger, while gas-poor galaxies may undergo a quieter transformation. This variability highlights the complex interplay of forces that drive starbursts, making each event unique. The aftermath of a starburst can be just as fascinating as the event itself. As the galaxy settles down, its newly formed stars begin to dominate its appearance and behavior. Massive stars, in particular, burn through their fuel quickly, ending their lives in spectacular supernova explosions. These explosions release vast amounts of energy, along with heavy elements that enrich the surrounding gas. Over time, this enriched material can mix with the galaxy's interstellar medium, fueling future generations of star formation. However, the intense feedback from supernovae and stellar winds can also expel gas from the galaxy entirely, effectively halting star formation in certain regions. This process, known as quenching, is a critical step in the evolution of many galaxies. Quenching transforms a once-active starburst galaxy into a more passive system, where little to no new star formation occurs. Quenched galaxies often take on a distinctive elliptical shape, as the lack of new stars leads to a more uniform distribution of older stars. This transition marks the end of the galaxy's most dynamic phase and the beginning of a quieter, more stable existence. One of the enduring mysteries of starbursts is their role in the cosmic star formation rate over time. Observations of distant galaxies have revealed that the universe's star formation rate peaked around 10 billion years ago, and has been declining ever since. Starbursts played a significant role during this peak period, driving much of the rapid star formation that characterized the early universe. However, as gas supplies dwindled and galaxies became more isolated, the frequency of starbursts decreased. Understanding this decline is a major goal of modern astrophysics, as it provides insight into the long-term evolution of the universe. Starbursts also have implications for the study of dark matter, the invisible substance that makes up most of the universe's mass. By analyzing the dynamics of starburst galaxies, scientists can infer the distribution of dark matter within them. For instance, the rotation curves of these galaxies reveal how mass is distributed, offering clues about the underlying dark matter halo. This connection between starbursts and dark matter is yet another example of how these events tie into the broader mysteries of the cosmos. In addition to dark matter, starbursts are linked to the study of cosmic dust. Dust plays a crucial role in star formation by cooling gas clouds and enabling them to collapse into stars. Starbursts produce enormous amounts of dust, which can obscure their inner workings from view. However, this same dust is also a valuable tool for astronomers. By studying the infrared radiation emitted by dust, scientists can map the distribution of star formation and gain a better understanding of the physical processes driving starbursts. Advancements in technology have made it possible to study starbursts in greater detail than ever before. Telescopes like the Atacama Large Millimeter/Submillimeter Array, ALMA, and the James Webb Space Telescope have revolutionized our ability to observe starbursts, allowing scientists to probe the dense, dusty regions where these events occur. These observations have revealed stunning details about the structure and dynamics of starburst galaxies, from the swirling motions of gas clouds to the formation of individual star clusters. Each new discovery adds another piece to the puzzle, bringing us closer to a complete understanding of these fascinating phenomena. Despite these advances, many questions about starbursts remain unanswered. For example, what determines the ultimate fate of a starburst galaxy? Why do some galaxies recover from starbursts and continue forming stars, while others become permanently quenched? And how do starbursts influence the larger-scale structure of the universe? These are the kinds of questions that drive ongoing research, pushing the boundaries of what we know about the cosmos. Starbursts are not isolated events. Their influence extends far beyond the boundaries of individual galaxies. One of the most intriguing aspects of starbursts is their impact on the cosmic web, the large-scale structure of the universe. The cosmic web consists of filaments of galaxies and intergalactic gas that stretch across vast distances, connecting clusters of galaxies like threads in a cosmic tapestry. Starbursts contribute to this web by enriching intergalactic space with heavy elements and injecting energy into the surrounding environment. This process, often referred to as Galactic feedback plays a crucial role in shaping the evolution of the universe. Galactic feedback from starbursts manifests in several forms, including supernova-driven winds, radiation pressure, and shock waves. These forces work together to push gas and dust out of the galaxy, creating massive outflows that can travel for hundreds of thousands of light years. Observations of starburst galaxies like M82 have revealed spectacular examples of these outflows, with streams of gas and dust extending far beyond the galaxy's central regions. These outflows not only regulate star formation within the galaxy but also influence the surrounding intergalactic medium, distributing metals and altering its temperature and density. The metals expelled by starbursts are particularly significant because they play a key role in the cooling of gas clouds. Metals like carbon, oxygen, and iron emit radiation that allows gas to lose heat and condense, facilitating the formation of new stars. Without these elements, the process of star formation would be far less efficient, and the universe would look very different. By enriching the intergalactic medium with metals, starbursts help to seed the next generation of star formation in other galaxies, contributing to the ongoing cycle of cosmic evolution. The energy injected by starbursts into the intergalactic medium also has a profound impact on the behavior of galaxy clusters. Galaxy clusters are the largest gravitationally bound structures in the universe, containing hundreds or even thousands of galaxies along with vast amounts of hot gas. The gas in these clusters is heated to extreme temperatures, emitting X-rays that can be detected by telescopes like Chandra and XMM Newton. Starbursts contribute to this heating process by releasing energy into the cluster environment, helping to maintain the high temperatures observed in these regions. Another fascinating connection between starbursts and the cosmic web is the phenomenon of cold gas accretion. As galaxies interact with the cosmic web, they draw in streams of cold gas from the intergalactic medium. This gas serves as fuel for star formation, replenishing the galaxy's reserves and sustaining starbursts over long periods. Observations of high redshift galaxies, those seen as they appeared billions of years ago, have provided compelling evidence for this process. These galaxies often exhibit intense starburst activity, fueled by the steady inflow of cold gas from the cosmic web. The interplay between starbursts and the cosmic web highlights the interconnected nature of the universe. Starbursts are not just local events confined to individual galaxies. They are part of a larger cosmic ecosystem, influencing and being influenced by their surroundings. This perspective underscores the importance of studying starbursts not only as isolated phenomena but also as integral components of the broader cosmic landscape. One of the most compelling aspects of starbursts is their potential to provide insight into the earliest stages of galaxy formation. In the early universe, just a few 100 million years after the Big Bang, the first galaxies began to form. These primordial galaxies were likely dominated by intense starburst activity, driven by the rapid accumulation of gas and the lack of stabilizing forces like magnetic fields and dark matter halos. By studying modern starbursts, astronomers can gain valuable clues about the conditions that prevailed during this formative period. For example, observations of distant starburst galaxies have revealed that they often exhibit irregular shapes and chaotic dynamics, resembling the predicted properties of early galaxies. These galaxies are characterized by clumpy regions of intense star formation, with little evidence of the well-organized structures seen in more mature systems like spiral galaxies. This chaotic appearance is a testament to the turbulent processes that dominated the early universe, from violent mergers to the rapid cooling of primordial gas clouds. The study of ancient starbursts is further enhanced by the use of gravitational lensing, a phenomenon predicted by Einstein's theory of general relativity. When light from a distant galaxy passes near a massive object, such as a galaxy cluster, the object's gravity bends and magnifies the light, effectively creating a natural telescope. This effect allows astronomers to study extremely distant starburst galaxies in unprecedented detail, revealing their internal structure and star formation activity. These observations provide a direct window into the early universe, offering a glimpse of the cosmic conditions that gave rise to the galaxies we see today. Starbursts also play a role in the reionization of the universe, a pivotal event that occurred about 13 billion years ago. During this epoch, the first stars and galaxies emitted intense ultraviolet radiation that ionized the surrounding hydrogen gas, transforming the universe from a neutral to an ionized state. Starburst galaxies are thought to have been major contributors to this process, as their massive stars produce the high-energy photons needed to drive reionization. By studying the properties of starburst galaxies at high redshifts, scientists hope to unravel the mysteries of this transformative period in cosmic history. Another intriguing aspect of starbursts is their potential connection to the formation of supermassive black holes. While it's well established that supermassive black holes exist at the centers of most galaxies, their origins remain a topic of intense debate. One hypothesis is that starbursts and black hole formation are closely linked, with the same processes that drive rapid star formation also fueling the growth of black holes. For example, the inflow of gas into the central regions of a galaxy during a starburst could feed the black hole, causing it to grow at an accelerated rate. Observations of distant quasars, extremely luminous objects powered by supermassive black holes, support this idea, as many quasars are associated with intense starburst activity. This connection between starbursts and black holes raises profound questions about the nature of galaxy evolution. Are starbursts a prerequisite for the formation of supermassive black holes, or are they simply a byproduct of the same underlying processes? And how do black holes, in turn, influence the galaxies that host them? These questions remain at the forefront of astrophysical research, driving new observations and theoretical studies. The interplay between starbursts and supermassive black holes introduces a fascinating feedback loop that shapes the evolution of galaxies over cosmic time. As starbursts drive gas and dust into the central regions of a galaxy, they fuel the growth of the central black hole. However, as the black hole accumulates mass, it begins to release immense amounts of energy in the form of radiation, relativistic jets, and powerful winds. This phenomenon, often referred to as active galactic nucleus (AGN) feedback, can have profound effects on the surrounding galaxy. AGN feedback is capable of halting star formation by heating or expelling the gas needed to create new stars. This process is evident in many elliptical galaxies, which show little to no ongoing star formation and are thought to have undergone intense periods of starburst and AGN activity in the past. The energy output from the black hole, fueled by the earlier starbursts, can effectively shut down the galaxy's ability to form stars, leaving behind a population of aging stars and little available gas. The relationship between starbursts and black holes also sheds light on the so-called M-sigma relation, a correlation observed between the mass of a galaxy's central black hole and the velocity dispersion of stars in its bulge. This relationship suggests a tight connection between the growth of black holes and the overall dynamics of their host galaxies. Starbursts may play a pivotal role in establishing this connection, as they regulate the inflow of gas and drive the processes that determine the eventual mass of the black hole and the structure of the galaxy. Another intriguing avenue of research is the connection between starbursts and the mysterious phenomenon of galactic winds. Galactic winds are large-scale flows of gas that escape from galaxies into intergalactic space. These winds are often driven by the combined effects of supernova explosions, stellar winds, and AGN activity, all of which are prominent in starburst galaxies. Galactic winds can carry vast quantities of gas, dust, and metals away from the galaxy, effectively redistributing material across cosmic distances. The metals carried by galactic winds contribute to the chemical enrichment of the intergalactic medium, influencing the properties of future generations of galaxies. These winds can also suppress star formation by removing gas from the galaxy, a process known as quenching. Quenching is a critical phase in galaxy evolution, as it marks the transition from a star-forming system to a more passive state. Understanding the role of starbursts in driving galactic winds is therefore essential for piecing together the life cycle of galaxies. Galactic winds also play a key role in the creation of large-scale structures known as superbubbles. Superbubbles are enormous cavities in the interstellar medium, formed by the combined energy of multiple supernovae and stellar winds from massive stars in a starburst region. These structures can span hundreds of light years and have a profound impact on the surrounding galaxy. The expanding edges of superbubbles compress nearby gas, potentially triggering new waves of star formation. At the same time, the interior of the superbubble can become a site for the mixing of gas and metals, altering the chemical composition of the galaxy. Starbursts are not only crucial for understanding the internal dynamics of galaxies but also for unraveling the mysteries of galaxy interactions and mergers. Many starbursts are triggered by interactions between galaxies, such as close encounters or outright collisions. These events disrupt the galaxy structures, funneling gas into their central regions and sparking intense episodes of star formation. The antennae galaxies, a pair of colliding galaxies located about 45 million light-years away, are a striking example of this phenomenon, with their overlapping structures and luminous starburst regions providing a dramatic visual testament to the power of galactic interactions. During these interactions, tidal forces play a critical role in redistributing gas and stars within the galaxies. Gas is often stripped from the outer regions of the galaxies and deposited into tidal tails, long streams of material that extend far into intergalactic space. These tails can serve as sites for new star formation, creating star clusters that may eventually evolve into dwarf galaxies. The interactions also drive the inflow of gas into the central regions of the galaxies, fueling both starbursts and the growth of supermassive black holes. The study of starbursts and interacting and merging galaxies provides valuable insights into the processes that drive galaxy evolution on cosmic timescales. Observations of distant galaxy clusters reveal that interactions were far more common in the early universe, when galaxies were closer together and the overall density of the universe was higher. These interactions likely played a major role in shaping the galaxies we see today, including our own Milky Way. Starbursts also have a unique role in the broader context of cosmic evolution, particularly in the transition from the blue cloud to the red sequence. In the color magnitude diagram of galaxies, the blue cloud represents star-forming galaxies, while the red sequence consists of more passive, elliptical galaxies. Starburst events often act as a bridge between these two populations, marking the final stages of star formation before a galaxy transitions to the red sequence. The quenching of star formation during or after a starburst is a key step in this transformation, driven by processes like AGN feedback, galactic winds, and the exhaustion of gas. The connection between starbursts and the larger-scale structure of the universe also extends to the phenomenon of cosmic reionization. During the epoch of reionization, the first galaxies and quasars emitted intense ultraviolet radiation that ionized the surrounding hydrogen gas, transforming the universe from a neutral to an ionized state. Starburst galaxies are believed to have been significant contributors to this process, as their massive stars produced the high-energy photons needed to reionize the intergalactic medium. Observations of distant starburst galaxies at high redshifts provide crucial clues about this pivotal period in cosmic history, helping to answer fundamental questions about the early universe. As we delve deeper into the mysteries of starbursts, it becomes increasingly clear that these events are far more than mere episodes of intense star formation. They are powerful engines of cosmic evolution, shaping galaxies, enriching the intergalactic medium, and driving the processes that define the structure and dynamics of the universe. By studying starbursts, we gain not only a deeper understanding of the life cycles of galaxies but also a glimpse into the origins of the cosmos itself, a story written in the light of the stars. The interplay between starbursts and their host galaxies extends into the realm of cosmic scales, revealing their profound influence on the universe's large-scale structure. Starbursts do not merely occur in isolation. They are often found in regions of high galaxy density, such as galaxy clusters and protoclusters. These environments serve as natural laboratories for understanding the connections between starbursts, galactic interactions, and the broader cosmic web. Galaxy clusters, which contain hundreds or thousands of galaxies bound together by gravity, often exhibit a dichotomy between active star-forming galaxies and more passive systems. Starburst galaxies within clusters stand out as rare but vital components. Their intense star formation rates may be triggered by processes unique to these environments, such as ram pressure stripping. As a galaxy moves through the dense intracluster medium, the gas within the galaxy is compressed or stripped away, potentially igniting bursts of star formation before the gas is fully removed. In addition to interactions within clusters, protoclusters, regions in the early universe destined to become massive clusters offer critical insights into the role of starbursts in cosmic evolution. Observations of protoclusters reveal galaxies in various stages of formation and interaction, many of which exhibit intense starburst activity. These regions provide a glimpse into the conditions of the early universe, where starbursts played a significant role in the assembly of large-scale structures. Starbursts also influence the intergalactic medium, IgM, on grand scales. The IgM, composed of diffuse gas that lies between galaxies, is the reservoir from which galaxies draw material for star formation. Conversely, galactic winds driven by starbursts enrich the IgM with metals, spreading elements like carbon, oxygen, and iron across vast distances. This process of metal enrichment has profound implications for the evolution of galaxies and the formation of stars, as metals affect the cooling and collapse of gas clouds. Furthermore, the energy released by starbursts and their associated feedback mechanisms can influence the temperature and density of the IgM. This interaction plays a role in regulating galaxy formation, as the heating of the IgM can suppress the infall of gas into galaxies, effectively limiting their star formation. The balance between these heating and cooling processes, mediated by starbursts, shapes the distribution of galaxies across cosmic time. The influence of starbursts extends even to the cosmic microwave background, CMB, the faint afterglow of the Big Bang. Intense star formation in the early universe can create sources of infrared radiation that are detectable as fluctuations in the CMB. By studying these fluctuations, astronomers can infer the properties of early starburst galaxies and their role in shaping the universe during its formative stages. Another intriguing aspect of starbursts is their connection to cosmic dust, a key component in the life cycle of stars and galaxies. Starburst regions are often enshrouded in thick clouds of dust, which absorb ultraviolet and visible light from young stars and re-emit it as infrared radiation. This process makes starbursts some of the most luminous infrared sources in the universe, allowing astronomers to study them even in distant galaxies. Dust plays a vital role in the cooling of gas clouds, facilitating the collapse of material to form new stars. However, the intense radiation from starbursts can also destroy dust grains, creating a delicate balance between the processes that promote and inhibit star formation. Understanding this interplay is essential for unraveling the complex dynamics of starburst regions and their impact on galactic evolution. The study of starbursts also intersects with the field of cosmology, particularly in the context of galaxy formation models. Simulations of galaxy evolution must account for the effects of starbursts, including their impact on the distribution of gas, stars, and dark matter. By comparing these models to observations, scientists can refine their understanding of how galaxies grow and evolve over time. One of the most exciting frontiers in the study of starbursts is the use of cutting-edge telescopes and instruments to probe these regions in unprecedented detail. The James Webb Space Telescope, JWST, for example, has opened new windows into the study of star-forming regions, allowing astronomers to observe the birth of stars and the dynamics of gas and dust with unparalleled clarity. Similarly, ground-based observatories equipped with advanced spectrographs enable detailed studies of the chemical composition and motion of starburst regions, providing crucial data for testing theoretical models. The exploration of starbursts is also deeply connected to the search for life beyond Earth. Starburst regions, with their abundance of newly formed stars and planets, offer unique environments for studying the conditions that may lead to the emergence of life. The chemical enrichment driven by starbursts introduces elements like carbon and oxygen into the interstellar medium, laying the groundwork for the formation of complex organic molecules. By studying these regions, scientists gain insights into the processes that may have shaped our own solar system and the potential for life elsewhere in the universe. Starbursts also inspire profound philosophical questions about the nature of the universe and our place within it. These events, which occur on timescales far beyond human experience, remind us of the dynamic and ever-changing nature of the cosmos. They challenge us to think about the interconnectedness of all things, from the smallest particles of dust to the largest structures in the universe. As we continue to study starbursts, we uncover new layers of complexity and beauty in the cosmos, These regions of intense star formation are not just transient events. They are fundamental processes that drive the evolution of galaxies and shape the universe as we know it. The story of starbursts is, in many ways, the story of the cosmos itself, a tale of creation, transformation, and endless wonder. Starbursts, as transformative events in galactic evolution, also offer a unique perspective on the interplay between the cosmos's micro and macro scales. At their heart, starbursts involve the smallest building blocks of galaxies, gas and dust, being reshaped into new stars, while their effects ripple outward to influence the largest cosmic structures. This duality underscores how seemingly localized phenomena can have far-reaching consequences across the universe. One of the most captivating aspects of starbursts is their ability to create extreme environments. Starburst galaxies often host regions where the physical conditions, such as density, pressure, and radiation intensity, are orders of magnitude greater than those in more typical star-forming areas. These extreme environments challenge our understanding of astrophysics, requiring new models and theories to explain the behaviors of matter under such intense conditions. For instance, the density of gas in starburst regions can be so high that it leads to rapid gravitational collapse, forming massive stars at a much faster rate than in calmer galactic environments. These massive stars, in turn, have short but powerful lifespans, ending in spectacular supernova explosions. The cumulative effect of these explosions generates shockwaves that compress surrounding gas, potentially triggering more star formation in a cascading cycle. However, these same shockwaves can also drive gas out of the galaxy, halting further star formation and shaping the galaxy's future evolution. The interplay between triggering and suppressing star formation in starbursts is a central theme in understanding their role in galactic evolution. This delicate balance depends on numerous factors, including the galaxy's initial gas reservoir, the intensity of feedback mechanisms, and the influence of external forces such as interactions with neighboring galaxies. By studying these factors, astronomers aim to unravel the complex processes that govern the life cycles of galaxies. Starburst-driven winds, often referred to as galactic superwinds, are among the most dramatic manifestations of feedback in these regions. These winds are propelled by the combined energy of supernovae, stellar winds, and intense radiation from young stars. They can reach velocities of hundreds or even thousands of kilometers per second, carrying vast amounts of gas and dust out of the galaxy. Observations of such winds in nearby starburst galaxies, like M82, have revealed their incredible power and extent, with streams of material stretching tens of thousands of light-years into intergalactic space. These superwinds play a crucial role in shaping the fate of both the host galaxy and its surroundings. By expelling gas, they can halt star formation within the galaxy, effectively quenching it and transitioning the galaxy from an active, star-forming state to a more passive one. At the same time, the ejected material enriches the intergalactic medium with metals and dust, seeding the surrounding environment with the ingredients necessary for future star and planet formation. The ability of starbursts to enrich the intergalactic medium ties directly into the broader narrative of cosmic chemical evolution. The universe began with only the lightest elements, hydrogen, helium, and trace amounts of lithium. All heavier elements, from carbon to iron to gold, were forged in the cores of stars and during supernova explosions. Starbursts, with their high rates of star formation and frequent supernovae, are hotspots for this chemical enrichment, accelerating the spread of these elements across the cosmos. This enrichment has profound implications for the formation of planets and, potentially, life. Elements like carbon, oxygen, and nitrogen are essential for organic chemistry, while others, like silicon and iron, are critical for building rocky planets. By spreading these elements far and wide, starbursts contribute to the diversity of planetary systems observed throughout the universe, including our own solar system. Another fascinating aspect of starbursts is their role in regulating the cosmic star formation rate over time. The universe's history is marked by a dramatic peak in star formation roughly 10 billion years ago, known as the cosmic noon. During this period, starburst activity was significantly more common than it is today, contributing to the rapid growth of galaxies. By studying starbursts in both the nearby and distant universe, astronomers can piece together the story of how galaxies transition from this highly active phase to the more quiescent state observed in many galaxies today. Starbursts also serve as natural laboratories for studying the extreme physics of star formation and feedback. For example, the intense radiation fields in starburst regions provide unique opportunities to study the interplay between light and matter. This includes processes like radiation pressure, where photons exert a force on gas and dust, and photoionization, where high-energy photons strip electrons from atoms. These processes are not only critical for understanding starburst dynamics but also have implications for broader astrophysical phenomena, such as the reionization of the universe during its early history. The study of starbursts is further enriched by the diversity of observational techniques used to explore them. Different wavelengths of light reveal different aspects of these regions, from the ultraviolet light of young, massive stars to the infrared glow of heated dust to the X-rays emitted by supernova remnants. By combining observations across the electromagnetic spectrum, astronomers can build a comprehensive picture of the complex interplay between stars, gas, and dust in starburst regions. One of the most exciting developments in recent years is the use of high-resolution simulations to model starburst activity. These simulations allow researchers to test hypotheses about the triggers of starbursts, the dynamics of star-forming regions, and the effects of feedback mechanisms. By comparing the results of these simulations with observations, scientists can refine their understanding of the physical processes driving starbursts and their role in galactic evolution. As our tools for studying starbursts continue to advance, so too does our appreciation for their significance in the broader context of the universe. These regions of intense star formation are not just local phenomena. They are key players in the cosmic story, influencing everything from the growth of galaxies to the distribution of elements to the potential for life itself. By unraveling the mysteries of starbursts, we gain deeper insights into the processes that have shaped the universe and our place within it. Starbursts also play a central role in advancing our understanding of galaxy morphology and structure. Over time, the feedback from starburst regions can lead to profound changes in the physical shape of a galaxy. For instance, in some cases, intense starburst activity can lead to the flattening or distortion of a galaxy's disk. This is often observed in interacting or merging galaxies, where the gravitational forces from their collision funnel gas into the core, triggering a central starburst. As this process unfolds, the gravitational dynamics and starburst-driven winds reshape the galaxy, sometimes forming features like tidal tails or irregular structures. Such transformations are key to understanding the Hubble sequence, the classification system for galaxies based on their shape, from ellipticals to spirals to irregulars. Many galaxies we see today with peculiar shapes owe their current forms to ancient starburst activity, often induced by galaxy interactions. This link between starbursts and galaxy morphology demonstrates how star formation is not just a byproduct of a galaxy's evolution, but a driving force in its structural and dynamical development. Another fascinating aspect of starbursts is their connection to black holes and active galactic nuclei, AGN. Many starburst galaxies are observed to host supermassive black holes at their centers. While the relationship between starbursts and AGN remains an area of active research, there is evidence that the two phenomena are closely linked. One possibility is that the same processes that drive gas into the galaxy's center to fuel a starburst also feed the central black hole, igniting AGN activity. Conversely, the energy output from the AGN, often in the form of powerful jets and winds, can influence the surrounding starburst region, either enhancing or suppressing star formation depending on the circumstances. This interplay between starbursts and AGN highlights the complex feedback loops that govern galaxy evolution. It also raises intriguing questions about the coevolution of galaxies and their central black holes. For instance, why do the masses of supermassive black holes correlate so strongly with the properties of their host galaxies, such as the mass of the central bulge? Starbursts may hold part of the answer, acting as a bridge between the small-scale physics of black hole accretion and the large-scale dynamics of galaxy growth. As we continue to explore starbursts, we also uncover their role in shaping the intergalactic environment. The material ejected by starburst-driven winds does not simply disappear, it becomes part of the intergalactic medium, IGM, the vast reservoir of gas that fills the space between galaxies. This material enriches the IGM with heavy elements, altering its composition and influencing subsequent galaxy formation. Observations of distant quasars, whose light passes through the IGM, reveal absorption lines that provide clues about the chemical makeup of this diffuse gas, much of which can be traced back to starburst activity. The ejection of material from starbursts also has implications for the cosmic web, the large-scale structure of the universe. This web consists of filaments of gas and dark matter that connect galaxies and clusters, with voids in between. Starbursts contribute to the enrichment of the filaments, creating localized pockets of higher metallicity that can seed the next generation of galaxy formation. By studying the interplay between starbursts and the cosmic web, astronomers gain insights into how galaxies are distributed and connected across the universe. On the observational front, new technologies are revolutionizing our ability to study starbursts in unprecedented detail. The James Webb Space Telescope, JWST, for example, offers unparalleled sensitivity in the infrared, allowing astronomers to peer through the dust that often obscures starburst regions. With its ability to resolve individual star-forming regions in distant galaxies, JWST is providing new insights into the triggers of starbursts, the properties of their stars, and the dynamics of their feedback processes. Similarly, radio telescopes like the Atacama Large Millimeter/Submillimeter Array, ALMA, are opening new windows into the cold molecular gas that fuels starbursts. By mapping the distribution and motion of this gas, ALMA helps researchers understand how starbursts are initiated and sustained. These observations are complemented by data from X-ray and gamma-ray telescopes, which reveal the high-energy processes associated with supernovae and stellar winds in starburst regions. Despite these advances, many questions about starbursts remain unanswered. For instance, what determines the duration of a starburst? Why do some galaxies experience multiple episodes of intense star formation, while others transition to a quiescent state after a single burst? How do environmental factors, such as interactions with neighboring galaxies or the influence of a galaxy cluster, shape the properties of starbursts? These questions drive ongoing research, as astronomers strive to build a more complete picture of the role of starbursts in galactic evolution. Starbursts also offer a unique perspective on the origins of cosmic diversity. The intense star formation and feedback processes in these regions create highly dynamic and varied environments, leading to a wide range of outcomes in terms of star and planet formation, chemical enrichment, and structural evolution. By studying starbursts across different types of galaxies and cosmic epochs, astronomers can better understand the factors that contribute to the incredible diversity of galaxies observed in the universe today. Moreover, starbursts provide a bridge between the past and the future of cosmic evolution. By studying nearby starburst galaxies, we gain insights into the processes that were more common in the early universe, when star formation rates were higher and galaxies were more dynamically active. At the same time, starbursts in the local universe serve as laboratories for understanding the conditions that may shape the future evolution of galaxies as they interact and merge. The significance of starbursts extends beyond astrophysics to touch on broader philosophical questions about our place in the cosmos. The elements produced in starburst regions, carbon, oxygen, nitrogen, and more, are the building blocks of life. By studying how these elements are created and distributed, we gain a deeper appreciation for the interconnectedness of the universe and the processes that make life possible. Ultimately, starbursts are a testament to the dynamic and ever-changing nature of the cosmos. They remind us that galaxies are not static entities but vibrant ecosystems, shaped by the interplay of matter, energy, and gravity. Through the study of starbursts, we uncover not only the story of galaxies but also the story of the universe itself, a story of creation, transformation, and the endless cycle of birth and renewal. The intricate dance of starbursts within galaxies and their far-reaching consequences challenges us to think about the universe as a dynamic system. Starbursts act as cosmic milestones, signaling periods of intense activity that ripple outward, influencing their surroundings in profound ways. This ongoing cycle of creation and destruction is at the heart of galactic evolution, offering glimpses into the forces that have shaped the cosmos over billions of years. One of the key aspects of starbursts is their ability to drive what astronomers refer to as galactic winds. These powerful outflows, composed of gas, dust, and high-energy particles, are propelled by the collective force of supernovae and stellar winds from massive stars. As this material is ejected into intergalactic space, it carries with it the chemical fingerprints of the galaxy it originated from. This has profound implications not only for the host galaxy but also for the intergalactic medium, IgM, which absorbs this material and becomes enriched with heavy elements. The importance of these galactic winds cannot be overstated. They serve as a mechanism for redistributing material throughout the universe. For instance, a starburst in one galaxy might eject gas and metals that later contribute to the formation of stars and planets in a neighboring galaxy. This interplay between galaxies is a cornerstone of cosmic evolution, demonstrating how interconnected the universe truly is. Another fascinating outcome of galactic winds is their impact on the host galaxy itself. By expelling gas, these winds can effectively regulate star formation, preventing a galaxy from depleting its gas reserves too quickly. This self-regulation mechanism ensures that star formation proceeds at a sustainable rate over time. However, in extreme cases, galactic winds can strip a galaxy of its star-forming material entirely, leading to a phase of quiescence where star formation nearly halts. These processes underline the dual role of starbursts as both creators and destroyers, capable of breathing life into a galaxy or shutting down its star-forming potential. As we delve deeper into the role of starbursts, we encounter their connection to galaxy mergers and interactions. When galaxies collide or pass close to one another, the resulting gravitational forces can compress gas clouds within the galaxies, triggering intense starburst activity. These interactions often lead to the formation of unique and stunning structures, such as tidal tails and bridges, which are visible markers of the galaxy's turbulent encounters. Studying these phenomena provides valuable insights into the dynamics of galaxy interactions and the processes that drive starburst activity. Interestingly, galaxy mergers are also linked to the formation of elliptical galaxies, which are typically composed of older stars and exhibit little ongoing star formation. During a merger, the intense starburst activity consumes much of the available gas, and the resulting feedback processes expel any remaining material. Over time, the merged galaxy settles into an elliptical shape, marking the end of its star-forming era. This transformation underscores the critical role of starbursts in determining the evolutionary pathways of galaxies. Beyond their influence on individual galaxies, starbursts are also crucial to understanding the broader context of cosmic history. Observations of distant starburst galaxies, which appear as luminous infrared objects, reveal that these phenomena were far more common in the early universe. This aligns with the cosmic star formation history, which shows that the rate of star formation peaked around 10 billion years ago, and has been declining ever since. By studying these ancient starbursts, astronomers can piece together a timeline of how the universe transitioned from its early, chaotic state to the more structured cosmos we see today. In this context, starbursts serve as a window into the past, allowing us to study the conditions that prevailed during the era of peak star formation. For example, the dense and turbulent environments of early starburst galaxies provide clues about the processes that led to the rapid assembly of stars and the buildup of galactic structures. These observations also inform models of galaxy formation and evolution, helping researchers refine their understanding of how the universe has changed over time. A particularly intriguing aspect of starbursts is their role in the formation of massive star clusters and globular clusters. These dense collections of stars are thought to form in the extreme conditions of starburst regions, where gas clouds are compressed to incredibly high densities. Once formed, these clusters can survive for billions of years, serving as relics of the galaxy's past. Studying them provides a glimpse into the conditions of ancient starbursts and the processes that governed star formation in the early universe. Moreover, starbursts have implications for the study of dark matter, the mysterious substance that makes up most of the universe's mass. The gravitational effects of dark matter influence the behavior of gas and stars and galaxies, shaping the conditions that lead to starbursts. Conversely, the energy released by starbursts can affect the distribution of dark matter within a galaxy, creating a complex feedback loop. By studying this interplay, astronomers hope to gain new insights into the nature of dark matter and its role in cosmic evolution. On the observational front, advances in technology continue to push the boundaries of what we can learn about starbursts. Instruments like the Extremely Large Telescope, ELT, and the Square Kilometre Array, SKA, promise to revolutionize our understanding of these phenomena, providing unprecedented resolution and sensitivity. These tools will enable researchers to study starbursts in greater detail than ever before, from their internal dynamics to their interactions with the surrounding environment. As we look to the future, one of the most exciting frontiers in starburst research is the study of their role in the reionization era, a period in the early universe when the first galaxies and stars ionized the neutral hydrogen that filled the cosmos. Starbursts in these early galaxies are thought to have been a major driver of reionization, producing the ultraviolet radiation needed to heat and ionize the surrounding gas. By studying the light from distant starburst galaxies, astronomers hope to unravel the mysteries of this pivotal epoch and its impact on the subsequent evolution of the universe. The study of starbursts is a testament to the interconnectedness of the cosmos. These regions of intense star formation are not isolated phenomena but integral components of the larger cosmic story. They link the birth and death of stars to the evolution of galaxies, the enrichment of the intergalactic medium, and the formation of planetary systems. Through their dynamic and transformative processes, starbursts illuminate the intricate web of relationships that govern the universe. In many ways, starbursts are the heartbeat of the cosmos, pulsing with the energy of creation and driving the cycles of growth and change that define our universe. Their study not only deepens our understanding of the physical processes that shape the cosmos but also inspires a sense of wonder about the beauty and complexity of the universe we inhabit. As we continue to explore these stellar phenomena, we are reminded of the boundless curiosity that drives human inquiry and the endless possibilities that await discovery. Starbursts are not merely local phenomena. They hold a universal significance in our quest to understand the broader processes of cosmic evolution. They illustrate the complex interplay between stellar birth, death, and the evolution of galaxies. These regions of intense star formation influence their galaxies in ways that extend far beyond the immediate environment, and in turn, these galaxies contribute to the overall structure and fate of the universe. As we delve into the science of starbursts, it's important to recognize the variety of starburst types that exist across the universe. The most extreme examples are found in what are called ultraluminous infrared galaxies, ULIRGs. These galaxies are characterized by incredibly high luminosities, many orders of magnitude greater than the Milky Way, and they are thought to be in the midst of massive starbursts, with the star formation rate reaching hundreds or even thousands of times that of the Milky Way. In these systems, the extreme levels of dust and gas play a pivotal role. The interstellar medium, made up of gas, dust, and other elements, serves as the fuel for star formation. In a starburst region, this material is compressed under intense gravitational forces, creating the perfect conditions for the rapid formation of new stars. However, these regions are also extremely energetic, with massive stars quickly expiring in supernovae, releasing copious amounts of energy and matter into the surrounding space. This process not only accelerates the evolution of the galaxy but also enriches the interstellar medium with heavier elements, such as carbon, oxygen, and iron, that are necessary for the formation of planets and life. Interestingly, the feedback from starbursts goes beyond the immediate effects of stellar winds and supernovae. The energy and momentum released during these events can influence the galaxy's large-scale structure, particularly in how it interacts with the surrounding environment. This feedback can affect the rotation curve of a galaxy, alter its morphology, and even influence the galaxy's eventual fate. For instance, the intense energy output during a starburst can lead to the ejection of gas from the galaxy, leading to a loss of material that would otherwise have contributed to future generations of stars. This process is thought to play a critical role in the transition from active, star-forming galaxies to passive, quiescent ones, such as elliptical galaxies. While starbursts can drive the rapid transformation of galaxies, they also reveal important insights into the timescales and nature of galactic evolution. The fact that starbursts can occur on relatively short timescales, usually only a few 100 million years, suggests that they are not a constant feature of a galaxy's evolution. Instead, starbursts are episodic, triggered by specific conditions such as galaxy mergers or encounters with other galaxies. This cyclical nature of star formation means that galaxies are constantly evolving, with new generations of stars being born, living, and dying in increasingly complex ways. Beyond the direct effects on galaxies themselves, starbursts have long-term consequences for the intergalactic medium, IgM. The material expelled during starbursts can travel far beyond the boundaries of the galaxy, enriching the IgM with metals and other elements that were previously confined to individual galaxies. This process of chemical enrichment plays a crucial role in the overall evolution of the universe. As gas is expelled and mixed into the broader cosmos, it contributes to the gradual buildup of the elements needed for the formation of new stars, galaxies, and even life. In fact, the chemical composition of the universe has been significantly shaped by starbursts. The very elements that make up the Earth, carbon, oxygen, nitrogen, and others, were once forged in the hearts of stars and spread throughout the universe during events like supernovae. Starbursts serve as key sites of this ongoing chemical enrichment, where elements heavier than hydrogen and helium are produced in large quantities. These elements are then incorporated into the next generations of stars and planetary systems, enriching the potential for the emergence of life. Without starbursts and the stellar processes they fuel, the universe would be a much less diverse and interesting place. One fascinating aspect of starburst regions is their relationship with the concept of galaxy morphology. The intense star formation occurring within these regions can significantly alter a galaxy's appearance. For instance, starbursts and spiral galaxies can transform them into what are known as starburst spirals, where the arms of the galaxy are dramatically brightened by the newly formed stars. These galaxies often display a level of brightness that far exceeds typical spiral galaxies, marking the moment of heightened activity in their evolutionary timeline. However, starbursts can also contribute to the formation of galaxies that are devoid of spiral arms. When a galaxy undergoes a particularly violent starburst event, such as a major merger with another galaxy, the resulting feedback can effectively quench star formation and leave behind a remnant galaxy with little or no star-forming activity. These galaxies, often referred to as red and dead galaxies, are typically elliptical in shape and contain very few young stars. While these galaxies may seem like the endgame of star formation, they represent just one possible outcome of the evolutionary journey that starburst galaxies undergo. The role of starbursts in galactic evolution is also tied to the larger-scale phenomenon of cosmic structure formation. As galaxies evolve, they do so within the broader context of the universe's large-scale structure, which is shaped by gravity, dark matter, and other fundamental forces. Starbursts act as pivotal moments in this ongoing process, influencing the shape and behavior of galaxies within galaxy clusters and superclusters. These regions of intense star formation are embedded within the larger cosmic web, where their evolution is governed by interactions with nearby galaxies, dark matter, and the expanding universe. One of the most profound implications of starburst regions is their role in the early universe. Observations of distant galaxies, particularly those from the Hubble Space Telescope and other advanced observatories, have revealed that starbursts were far more common during the first few billion years of the universe's existence. This period, often referred to as the cosmic noon, represents a time when galaxies were undergoing their most intense periods of star formation. During this era, starbursts helped to fuel the rapid growth of galaxies, contributing to the assembly of the cosmic structures we observe today. As we look at starbursts in the early universe, we gain valuable insights into the processes that shaped the formation of the first galaxies. The extreme environments of these ancient starburst galaxies provide a snapshot of a time when the universe was in a state of heightened activity. By studying these distant, early starbursts, astronomers hope to unlock the mysteries of galaxy formation and the conditions that led to the establishment of the cosmic structures we see today. In terms of technological advancements, the next generation of telescopes and observatories will allow us to probe starbursts in unprecedented detail. Instruments such as the James Webb Space Telescope, JWST, which is set to observe galaxies at even greater distances, will provide new insights into the role of starbursts in galaxy evolution. These observations will allow us to peer deeper into the universe's past, uncovering the hidden mechanisms of star formation and the processes that govern galaxy dynamics. Ultimately, the study of starbursts is a journey of discovery, offering a deeper understanding of the forces that drive the evolution of galaxies and the cosmos itself. By unlocking the mysteries of these stellar nurseries, we gain a greater appreciation for the intricate and interconnected processes that shape the universe. Starbursts are not just events in the life of a galaxy. They are fundamental building blocks of cosmic history, shaping the destiny of galaxies, enriching the intergalactic medium, and contributing to the very elements that make life possible. As we continue to explore the nature of starbursts, one thing becomes abundantly clear. These regions of intense activity are central to the ongoing narrative of galactic evolution. They embody the cycles of birth and death, creation and destruction, that govern the cosmos. In the years to come, as we develop more advanced tools to study the farthest reaches of space, starbursts will remain a focal point of our quest to understand the universe's most profound mysteries. The significance of starbursts extends beyond just their impact on the galaxies in which they occur. These regions of intense star formation contribute to a larger, dynamic picture of the universe, affecting everything from the distribution of matter in the cosmos to the formation of planetary systems. The energy released by starbursts influences the evolution of the galactic environment, causing ripples that propagate across vast cosmic distances. One critical aspect of this influence is the role starbursts play in the intergalactic medium, IGM. The material ejected by supernovae and stellar winds within starburst regions not only affects the immediate vicinity of the galaxy but also enriches the broader space between galaxies. This process of chemical enrichment of the IGM helps shape the evolution of galaxies and the overall chemical composition of the universe. In starburst regions, large amounts of gas are converted into new stars, but these stars often have relatively short lifespans. Once they exhaust their nuclear fuel, they end their lives in explosive supernovae. These explosions release vast amounts of energy, which can expel gas and dust into the surrounding space, enriching the IGM with metals and other elements formed in the cores of the stars. This transfer of material to the IGM is crucial for the ongoing evolution of the universe, as it ensures that new generations of stars are born from a progressively richer mixture of elements, which in turn contributes to the creation of planets, moons, and potentially even life itself. The intergalactic medium plays a key role in the larger structure of the universe. As gas and dust are expelled during starbursts, they mix with the surrounding space, creating a more uniform distribution of material across vast distances. This material can eventually clump together due to the force of gravity, eventually forming new galaxies and clusters of galaxies. The interaction between starburst regions and the IGM thus contributes to the larger-scale cosmic structure, helping to shape the web of galaxies that make up the observable universe. While starbursts are typically associated with galaxy mergers or interactions, the occurrence of starbursts in isolated galaxies offers important clues about the conditions required for such explosive periods of star formation. In some cases, even without interactions with other galaxies, isolated galaxies can experience intense starbursts. This suggests that there are additional factors at play, such as the availability of gas and dust, that can trigger such periods of activity. As astronomers continue to study these phenomena, they are uncovering new insights into the complex processes that govern the birth and death of stars, the evolution of galaxies, and the ongoing enrichment of the universe. One of the most fascinating aspects of starburst galaxies is their role in the evolution of galaxy morphology. The intense star formation in these galaxies can significantly alter their structure over relatively short timescales. In spiral galaxies, starbursts can trigger the formation of bright, star-filled arms, altering the appearance of the galaxy. In more extreme cases, such as during major galaxy mergers, starbursts can result in the complete destruction of a galaxy's spiral structure, leaving behind an elliptical galaxy that has little to no star-forming activity. These morphological changes offer valuable clues about the processes that govern galaxy evolution, highlighting the dynamic and ever-changing nature of the cosmos. Starbursts also play a pivotal role in the ongoing study of galaxy formation. By examining distant galaxies in the early universe, astronomers can observe the role starbursts played in the formation of galaxies during a time when star formation rates were much higher. During this era, often referred to as cosmic noon, starbursts were a common feature in galaxies, driving the rapid assembly of galactic structures. By studying the characteristics of these early starbursts, scientists can gain a better understanding of the conditions that led to the formation of the first galaxies and the processes that shaped the structure of the universe as we know it today. Interestingly, the study of starbursts can also provide insights into the role of dark matter in galaxy formation. Dark matter, which makes up a significant portion of the total mass of the universe, does not interact with light in the same way as ordinary matter. However, its gravitational influence is critical in shaping the formation of galaxies. In starburst galaxies, the presence of dark matter can affect the dynamics of the galaxy, including the way in which gas is funneled into the central regions of the galaxy to fuel the starburst. By studying the interactions between starbursts and dark matter, astronomers are gaining valuable clues about the elusive nature of dark matter and its role in the formation and evolution of galaxies. As we continue to improve our observational capabilities, particularly with the upcoming generation of space telescopes such as the James Webb Space Telescope, JWST, we will gain new insights into the mysteries of starbursts. These advanced instruments will allow astronomers to observe starbursts in greater detail and at greater distances, providing a clearer picture of how starbursts have shaped the history of the universe. For example, the JWST will be able to observe galaxies that formed in the very early stages of the universe, allowing us to see starbursts in their infancy and providing a snapshot of the cosmic environment during key moments in the history of galaxy formation. One of the most exciting aspects of studying starbursts is the potential for discovering new types of galaxies that have yet to be fully understood. As our observational techniques improve, we may uncover new, previously unknown types of starburst galaxies that exhibit behaviors and properties that challenge our current understanding of galactic evolution. This ongoing exploration of the universe promises to uncover even more fascinating details about the processes that drive the evolution of galaxies and the larger structure of the cosmos. At the heart of all this lies the fact that starbursts are not isolated events. They are an intrinsic part of the larger cosmic cycle. Starbursts are born from the collapse of gas and dust within galaxies, and their energy and material continue to shape the environment long after the stars themselves have passed away. The legacy of starbursts lives on in the remnants of supernovae, in the distribution of elements across the universe, and in the continued formation of galaxies and stars. They represent a fundamental piece of the puzzle in understanding the vast and ever-changing universe we live in. As we continue to investigate these stellar phenomena, one thing is clear: the study of starbursts will remain a crucial part of the journey to uncover the mysteries of the cosmos. These regions of intense star formation provide a window into the forces that shape galaxies, the elements that fuel life, and the complex interactions that govern the evolution of the universe. The more we learn about starbursts, the closer we come to understanding the very nature of the universe itself. With each discovery, we are reminded of the interconnectedness of all things in the cosmos, and the role that starbursts play in the ongoing story of the universe's evolution. The study of starbursts also plays a significant role in our understanding of galaxy quenching, a process by which galaxies stop forming new stars. As galaxies evolve, many of them experience a transition from active, star-forming regions to quiescent, passively evolving ones. This process is of great interest to astronomers, as it reveals the complex interactions between galaxies and their environments. Starbursts offer a fascinating glimpse into the factors that may trigger or halt this transformation. In some cases, starbursts can actually lead to the quenching of star formation. The intense activity associated with a starburst can result in the expulsion of large amounts of gas from the galaxy, which is crucial for fueling further star formation. If a galaxy runs out of its gas supply, whether due to the feedback from starbursts or external environmental factors, it can no longer sustain the birth of new stars, causing it to enter a quiescent phase. Understanding how starbursts contribute to this process helps astronomers piece together the puzzle of galaxy evolution, and why some galaxies transition into their quiet, mature states. On the other hand, The material expelled during a starburst can also lead to the formation of new galaxies or the rejuvenation of galaxies that had previously stopped forming stars. This feedback mechanism helps to regulate the rate at which galaxies evolve, creating a balance between active and quiescent phases. By studying the interplay between starbursts and galaxy quenching, scientists gain valuable insights into how galaxies maintain their vitality over time and how the universe's cosmic landscape changes over billions of years. An essential part of this feedback cycle is the role of supernovae. When massive stars explode in a starburst region, they release huge amounts of energy, along with heavy elements synthesized during their lifetimes. These supernovae not only produce the explosive forces that push gas out of the galaxy but also contribute to the chemical enrichment of the surrounding environment. The metals produced in supernovae, such as iron, silicon, and oxygen, are vital for the creation of planets, and their distribution into the intergalactic medium helps seed the next generation of stars and galaxies. This stellar recycling process ensures that the elements necessary for the formation of life are perpetually created and redistributed across the universe. Moreover, starbursts contribute to the enrichment of the galactic halo. The halo of a galaxy is a vast, diffuse region of stars, gas, and dark matter that surrounds its disk. Although it's not as well understood as the central bulge or the spiral arms, the galactic halo is an important component in the evolution of a galaxy. The gas expelled during a starburst, along with the material ejected by supernovae, helps enrich the halo with heavier elements, thereby affecting the future generations of stars that form in this region. The presence of these enriched elements also allows astronomers to trace the history of star formation and the dynamics of the galaxy as a whole. When studying starbursts, astronomers often look at galaxies that exhibit these intense star-forming activities at different stages of their evolution. This is crucial because it allows scientists to observe the evolutionary trajectory of galaxies, from their early stages of rapid star formation to their later, more quiescent periods. By studying the chemical composition, structure, and dynamics of starburst galaxies at various stages, researchers can build more detailed models of galaxy formation and evolution. These models are essential for understanding the broader context of the universe's development, including the transition from the cosmic dawn, a time when the first stars and galaxies formed, to the cosmic present we observe today. Another exciting aspect of starburst galaxies is their potential for hosting active galactic nuclei, AGN. An AGN is a supermassive black hole at the center of a galaxy that is actively accreting matter. The intense gravitational pull of the black hole creates an accretion disk of hot, ionized gas that emits enormous amounts of energy, often outshining the rest of the galaxy. In some starburst galaxies, the combination of intense star formation and the presence of an AGN can lead to unique and extreme conditions. The interplay between the central black hole and the surrounding star-forming region creates a dynamic, energetic environment that can have significant effects on the galaxy's evolution. The relationship between starbursts and AGN is a subject of ongoing research, as it is not fully understood how these two phenomena influence each other. It's possible that the energy output from the AGN could regulate the rate of star formation in the surrounding galaxy, either quenching or enhancing it depending on the balance between the two forces. Alternatively, the intense gas flows from a starburst could fuel the central black hole, leading to increased activity in the AGN. Understanding this relationship is crucial for unraveling the complex processes that govern the growth of galaxies and supermassive black holes. One aspect of starburst galaxies that often captures the imagination of astronomers is their potential to host unusual or extreme types of stars. For example, starbursts can give rise to extremely massive stars, sometimes called hypernova progenitors. These stars are much larger than typical massive stars, and their eventual explosions can release far more energy than a standard supernova. Such stars play a significant role in the enrichment of the galaxy and the intergalactic medium, as they can expel heavier elements into space in a much more dramatic manner than ordinary stars. The study of these extraordinary stars is a fascinating avenue of research, as they may provide insights into the most extreme conditions of star formation and stellar evolution. Furthermore, starbursts in distant galaxies, those located billions of light-years away, offer a unique glimpse into the universe's past. Since light takes time to travel across vast distances, observing distant galaxies allows us to look back in time, effectively giving us a snapshot of the universe as it was long ago. By studying the starburst activity in these distant galaxies, astronomers can learn more about the conditions that prevailed during different epochs of the universe's history. This is particularly important when studying the cosmic dawn period, a time when the first galaxies and stars began to form. Starbursts, as key events in the life cycle of galaxies, can provide valuable clues about the environment in which the first galaxies formed and how the universe transitioned from a dark, featureless expanse to the rich, complex structure we observe today. As our observational tools improve, particularly with the advent of more advanced space telescopes like the James Webb Space Telescope, JWST, we will be able to study starbursts with greater precision. The JWST's ability to observe distant galaxies in infrared wavelengths will allow astronomers to peer through the cosmic dust that often obscures our view of star-forming regions. This will enable us to study the detailed processes occurring in starburst galaxies that were previously hidden from view. With these new tools, we are poised to unlock many more secrets about the role starbursts play in the evolution of galaxies and the broader universe. Starburst galaxies not only provide insight into the evolution of galaxies but also offer clues about the processes that shape the structure and dynamics of the universe. One of the most fascinating aspects of starburst activity is its impact on the intergalactic medium, IGM, the vast, nearly empty space between galaxies. The IGM consists primarily of diffuse gas, most of it hydrogen, and its interaction with starburst regions can lead to significant changes in the overall cosmic environment. When a galaxy undergoes a starburst, the intense radiation and energetic particles generated by the newborn stars can influence the surrounding intergalactic gas. This influence is especially strong in the early universe, when starburst activity was much more common, and the IGM was less enriched with heavier elements. The outflows of gas and radiation from starburst galaxies can heat, ionize, and chemically enrich the IGM, playing a crucial role in the overall evolution of the universe's large-scale structure. One of the mechanisms through which starbursts influence the IGM is through galactic winds. These winds are driven by the powerful supernova explosions that occur within starbursts. These explosions generate shock waves that push gas away from the galaxy, carrying with it the heavy elements created by dying stars. The expelled material can travel vast distances, spreading the chemical fingerprints of starburst regions across the universe. This process is essential for understanding the distribution of elements in the universe, as it helps to seed the IGM with the building blocks of life, elements such as carbon, oxygen, and nitrogen. Moreover, the outflows from starbursts can also affect the dynamics of the galaxy itself. As gas is expelled, the galaxy experiences a loss of mass, which can have profound consequences on its future evolution. In some cases, this mass loss can cause a galaxy to undergo a transformation, from a star-forming, gas-rich system to a gas-poor, quiescent one. This process is thought to be one of the primary drivers of galaxy quenching, and studying how starbursts contribute to this phenomenon helps astronomers understand the factors that lead to the cessation of star formation in galaxies. The role of starbursts in galactic evolution is not limited to their direct impact on the galaxy and the IGM. They also play a significant role in the formation and evolution of galaxy clusters. Galaxy clusters are large structures composed of hundreds to thousands of galaxies bound together by gravity, and they represent the largest gravitationally bound objects in the universe. The interaction between galaxies within a cluster can trigger starbursts, as gravitational forces can compress gas and fuel intense episodes of star formation. In the context of galaxy clusters, starbursts can also influence the intracluster medium, ICM, the hot, diffuse gas that permeates the space between galaxies in a cluster. The energy from starburst-driven outflows can heat the ICM, preventing the gas from cooling and collapsing into new stars. This heating process is thought to play a key role in regulating the star formation rates of galaxies within clusters, as the hot ICM acts as a cocoon that suppresses star formation. The interplay between starbursts and the ICM is an important aspect of understanding the dynamics of galaxy clusters and the evolution of galaxies within them. One of the most intriguing aspects of studying starbursts in distant galaxies is the way they help us probe the conditions of the early universe. Since starbursts are often associated with young, actively forming galaxies, their study provides a window into the processes that occurred during the cosmic dawn, an epoch that occurred just a few 100 million years after the Big Bang. By observing starburst galaxies at high redshifts, astronomers can investigate the conditions that led to the formation of the first galaxies and stars. The most ancient starbursts are believed to have occurred during the so-called epoch of reionization, a period when the first stars and galaxies began to ionize the hydrogen gas that filled the universe. This process, known as reionization, marks a pivotal moment in cosmic history, as it transformed the universe from a neutral state to one in which matter could interact with light. Starbursts played a significant role in this process, as the intense radiation from newly formed stars would have contributed to the ionization of hydrogen and the eventual clearing of the cosmic fog. As we look farther back into the universe's history, starbursts give us a glimpse of the earliest, most extreme environments that shaped the formation of galaxies and the larger cosmic structure. These extreme environments are important not only for understanding the evolution of galaxies but also for shedding light on the fundamental processes that govern the universe as a whole. The discovery and study of starburst galaxies are not limited to the observation of distant, high redshift systems. Modern observational techniques have also allowed scientists to explore starburst regions within our own Milky Way galaxy. Our galaxy hosts several starburst-like regions, including the well-known starburst ring around the center of the galaxy, where intense star formation is occurring. Observations of these regions give us a unique opportunity to study starbursts in a nearby, relatively familiar environment, offering valuable insights into the dynamics of star formation and the behavior of the interstellar medium. One particularly intriguing aspect of starbursts within the Milky Way is the potential for these regions to evolve into powerful, galaxy-wide phenomena known as galactic winds. These winds, which are driven by the collective energy of supernovae and the intense radiation from massive stars, can expel large amounts of gas from the galaxy, potentially quenching star formation or redistributing material within the galaxy. The study of these galactic winds can provide crucial clues about the ultimate fate of our own galaxy and the processes that regulate star formation on cosmic scales. Furthermore, studying starbursts in the Milky Way offers a chance to explore the intricate relationship between different phases of the interstellar medium. The interstellar medium is a complex and dynamic environment, consisting of gas, dust, and magnetic fields that interact in ways that are not yet fully understood. Starbursts provide an opportunity to study the interplay between these components, as the intense energy from newly formed stars can drive turbulence, compressions, and shocks within the surrounding gas. Understanding how these processes unfold can help astronomers piece together the broader picture of galaxy evolution, from the formation of individual stars to the evolution of entire galactic systems. As technology continues to advance, future space missions will further our understanding of starbursts and their role in the evolution of galaxies. Upcoming observatories, such as the James Webb Space Telescope, JWST, will allow astronomers to observe starburst galaxies in greater detail and at even higher redshifts, providing unprecedented insights into the conditions of the early universe. Additionally, the next generation of ground-based observatories, such as the Extremely Large Telescope, ELT, and the 30-meter telescope, TMT, will provide enhanced capabilities for studying the intricate dynamics of star-forming regions and their impact on galactic evolution. With these cutting-edge tools, astronomers will be able to delve deeper into the mysteries of starbursts and their influence on galaxy formation, evolution, and the larger cosmic structure. The answers we uncover in the coming decades will not only shape our understanding of galaxies but also provide critical insights into the fundamental forces that drive the evolution of the universe itself. The future of starburst research is exciting, as it holds the potential to reveal more about the intricate mechanisms that drive the universe's evolution. These extreme regions of star formation serve as natural laboratories for studying a range of astrophysical processes, from the birth of stars to the formation of the heaviest elements. They also provide an opportunity to probe the physical conditions of distant galaxies, which would otherwise be impossible to observe in detail. One of the key aspects that astronomers are eager to explore is the connection between starbursts and the formation of supermassive black holes. In many galaxies, especially those that exhibit intense star formation, there is evidence suggesting that supermassive black holes are actively growing at the centers of these systems. Some scientists theorize that starbursts could play a role in fueling the growth of these black holes. The energy released from the formation of massive stars, combined with the gravitational forces at play within these regions, could help drive the material towards the galactic center, where it may eventually be consumed by a growing black hole. Understanding this relationship is crucial not only for learning about the behavior of black holes but also for providing insights into how galaxies evolve over time. The growth of supermassive black holes is thought to be tied to the overall development of their host galaxies, influencing the rate of star formation and the dynamics of the galaxy as a whole. By studying starbursts in conjunction with the growth of supermassive black holes, astronomers can begin to unravel the complex feedback mechanisms that govern the evolution of both individual galaxies and large-scale cosmic structures. The chemical enrichment of galaxies is another vital aspect of starbursts that deserves further exploration. The rapid star formation seen in starburst regions leads to the creation of large quantities of heavy elements, such as carbon, oxygen, and iron. These elements are crucial for the development of life as we know it, and they also serve as a key signature of cosmic evolution. By studying the chemical composition of starburst galaxies, scientists can better understand the processes that led to the enrichment of the universe and the formation of the elements that make up stars, planets, and even life itself. One important question that arises when examining the chemical enrichment of starburst galaxies is how long this process continues. Some starbursts are short-lived, lasting only a few tens of millions of years, while others can last much longer. The duration of a starburst can have significant implications for the level of chemical enrichment that occurs within the galaxy. If the starburst is short-lived, it may not have enough time to produce large quantities of heavy elements, whereas a more prolonged starburst could enrich the galaxy more fully. The study of starburst duration and its impact on chemical enrichment is a key focus of ongoing research, as it helps to refine our understanding of galaxy evolution and the distribution of elements in the universe. In addition to chemical enrichment, starbursts also contribute to the production of cosmic dust. As massive stars evolve and die, they expel material into the surrounding environment, which can condense into dust. This dust plays a crucial role in the cooling and the evolution of the interstellar medium. It also helps to shield newly forming stars from the intense radiation produced by their more massive neighbors. The dust produced in starbursts can therefore help regulate star formation, as it absorbs and redistributes energy within the galaxy, influencing both the growth of new stars and the overall dynamics of the galaxy. One of the more mysterious and intriguing aspects of starbursts is their connection to the phenomenon of cosmic rays. Cosmic rays are high-energy particles that travel through space at nearly the speed of light. They are believed to be produced in extreme environments, such as supernova remnants and active galactic nuclei. Starbursts, with their intense supernova activity and high-energy environments, are thought to be major contributors to the production of cosmic rays. The study of cosmic rays in starburst galaxies is an area of active research, as these high-energy particles can provide valuable information about the processes occurring within star-forming regions. Cosmic rays interact with the gas and dust in these regions, influencing the chemistry of the interstellar medium and contributing to the overall dynamics of the galaxy. They may also play a role in the acceleration of charged particles, which can have important implications for the behavior of galaxies and their environments. Looking further into the future, the next generation of astronomical surveys will offer a more comprehensive understanding of the role of starbursts in galactic evolution. Large-scale surveys of the distant universe will provide detailed observations of starburst galaxies at various stages of their development. These observations will be crucial for mapping the history of star formation in the universe, revealing how different types of starburst galaxies evolve over cosmic time. One such survey, the upcoming Euclid mission, will provide high-precision measurements of the geometry of the universe, as well as the distribution of galaxies and their properties. By combining data from Euclid with observations from other next-generation telescopes, such as the JWST, astronomers will be able to study starbursts in unprecedented detail. These missions will help answer key questions about the frequency of starbursts, the conditions that trigger them, and their impact on galaxy evolution. As we continue to refine our models of star formation and galaxy evolution, starbursts will remain a crucial piece of the puzzle. They represent a link between the early, chaotic stages of galaxy formation and the more stable, mature galaxies that populate the universe today. By studying starbursts, we not only gain insight into the processes that shape the universe's structure but also learn about the fundamental forces that drive the creation and evolution of galaxies. Starbursts remind us of the extreme beauty and complexity of the universe, with each intense burst of stellar birth offering a fleeting yet powerful glimpse into the forces that shape the cosmos. As we observe these dynamic regions, for now, starburst galaxies remain one of the most fascinating and mysterious areas of astrophysical research. The answers they hold will continue to shape our understanding of the universe for years to come. And as technology advances, the ability to observe and study starburst regions will only improve, allowing us to unlock even more of the mysteries that lie at the heart of these stellar nurseries. As we push the boundaries of our technological capabilities, our understanding of starbursts and their role in galactic evolution will likely expand dramatically. Observing starbursts in different stages of their life cycle will provide us with clues not only about the formation of individual galaxies, but also about the larger processes that shape the universe on the grandest scales. These observations will likely challenge existing theories and provide new frameworks for understanding cosmic evolution. One promising avenue for future research is the study of the interaction between starburst galaxies and their surrounding environments. In many cases, these regions of intense star formation are not isolated. They are often embedded within larger galactic structures, such as galaxy clusters or superclusters. The dynamics of these interactions could provide valuable insights into the mechanisms that drive galactic evolution. For example, when a starburst galaxy interacts with a neighboring galaxy, it can lead to a transfer of gas and dust, which can, in turn, fuel or suppress star formation. These interactions could also trigger new rounds of starbursts, or even disrupt the existing stellar population. Understanding how these interactions shape star formation and the evolution of galaxies will be an essential part of future research. On the scale of cosmic time, starbursts represent a fleeting but intense period of activity in a galaxy's life. For many galaxies, starbursts are a one-off event, occurring during a period of rapid gas inflow or after a merger with another galaxy. However, in some galaxies, star formation continues at a high rate over extended periods, with starbursts recurring as the galaxy's gas supply is replenished. This could be due to continuous inflow of gas from the intergalactic medium, or due to the gravitational interactions between galaxies in a group or cluster. In these cases, starbursts may play an ongoing role in the galactic evolution process, influencing not only the stars and stellar populations but also the overall structure of the galaxy. The impact of starbursts on a galaxy's long-term evolution can also be seen in terms of its overall morphology. Starbursts can leave a lasting imprint on the galaxy's shape and structure. In some cases, the intense radiation and stellar winds produced by a starburst can drive the gas and dust out of the galaxy, creating an outflow that alters the galaxy's size and shape. These outflows, known as galactic winds, are thought to be responsible for the removal of a significant portion of the galaxy's gas, which can suppress future star formation. On the other hand, some of the gas expelled during a starburst can be recycled back into the galaxy, potentially triggering new cycles of star formation in the future. The intricate balance between gas inflows, outflows, and recycling plays a crucial role in determining the fate of a galaxy after a starburst event. Another area that is poised for exploration is the role of magnetic fields in starburst galaxies. Magnetic fields are known to play a significant role in the dynamics of the interstellar medium, influencing the behavior of gas and dust and potentially affecting star formation processes. The strength and configuration of magnetic fields in starburst galaxies could provide insights into the physical conditions that drive these intense periods of star formation. Understanding the relationship between magnetic fields, gas flows, and star formation in starburst regions is a complex but crucial aspect of understanding the broader evolution of galaxies. In recent years, astronomers have begun to employ a variety of observational techniques to study the magnetic fields in starburst galaxies. These methods include radio wavelength observations, which can reveal the structure and intensity of magnetic fields, and polarized light measurements, which provide clues about how the magnetic fields interact with the surrounding gas. As we continue to develop more advanced instruments and techniques, our ability to probe these magnetic fields with greater precision will allow us to gain deeper insights into the role they play in shaping star formation and galaxy evolution. A significant challenge in the study of starbursts is understanding their relationship with active galactic nuclei, AGN. An AGN is a region at the center of a galaxy that is extremely bright due to the accretion of material by a supermassive black hole. In many cases, AGNs are found in galaxies that also exhibit intense star formation, creating a complex environment in which both the formation of new stars and the growth of a supermassive black hole occur simultaneously. This raises important questions about how these two processes interact. Some theories suggest that the energy released by the AGN may help to regulate star formation by heating the surrounding gas, making it less likely to collapse into new stars. Others propose that the growth of the black hole could be fueled by the intense star formation occurring in the surrounding galaxy. Understanding the relationship between starbursts and AGNs is a key area of research because it could provide important clues about how galaxies evolve over time. It may also help to explain the observed correlation between the mass of a galaxy's supermassive black hole and the properties of its stellar population. This connection between black holes and stars is a central piece of the puzzle when it comes to understanding how galaxies develop and mature. As our ability to observe galaxies in greater detail improves, we will gain a more nuanced understanding of the delicate balance between star formation and black hole growth in these complex environments. Starbursts are also crucial for understanding the role of dark matter in galactic evolution. Dark matter, the mysterious substance that makes up most of the mass in the universe, is thought to play a key role in shaping the formation and structure of galaxies. Starbursts, by driving large amounts of gas into the center of a galaxy, can influence the distribution of dark matter within that galaxy. Observing how dark matter behaves in starburst galaxies could provide valuable insights into the nature of dark matter itself. This could help us unravel one of the greatest mysteries in astrophysics and bring us closer to understanding the fundamental components of the universe. The study of starbursts, therefore, is not only about understanding the processes that govern star formation but also about piecing together a larger picture of how galaxies evolve and how the universe itself is structured. As we continue to make breakthroughs in observational techniques, such as using next-generation telescopes like the James Webb Space Telescope, JWST, and the upcoming Extremely Large Telescope, ELT, our ability to study distant starburst galaxies with unprecedented precision will open up new avenues of discovery. With these advancements, we will be able to investigate starbursts not only in the nearby universe but also in the very distant past, when the first galaxies were forming. This will allow us to trace the evolution of galaxies from their earliest stages and provide valuable clues about the origins of star formation and the development of the cosmic structures that we see today. As we push the limits of what we can observe, we will be able to answer fundamental questions about the nature of the universe and our place within it. The study of starbursts is a journey that takes us from the birth of individual stars to the evolution of entire galaxies, offering insights into the processes that drive the universe's most spectacular phenomena. Whether it's through the creation of new elements, the fueling of supermassive black holes, or the formation of cosmic structures, starbursts are at the heart of many of the most profound questions in modern astrophysics. As our understanding of these extreme regions of star formation deepens, we are sure to uncover even more mysteries that will shape our view of the cosmos for generations to come. As we move forward into the next era of astronomical discovery, the potential for further breakthroughs in our understanding of starbursts continues to grow. With advancements in both observational technologies and computational modeling, we are now able to study starburst galaxies in unprecedented detail, unraveling the complexities of their role in galactic evolution. However, the questions surrounding starbursts are far from fully answered, and each new discovery brings with it more intrigue and more mysteries to explore. One of the most promising areas of research is the investigation of the connection between starbursts and the broader cosmic environment. Galaxies do not exist in isolation. They are part of vast cosmic networks, such as groups, clusters, and superclusters. Understanding how starbursts are influenced by the larger structures in which they are embedded is a critical part of deciphering the full story of galaxy evolution. This involves examining how galaxies interact with one another, and how the surrounding dark matter halos and gas reservoirs contribute to the conditions that spark starbursts in the first place. Recent discoveries have shown that starbursts can be triggered by external factors, such as the gravitational influence of a nearby galaxy. This is particularly evident in galaxy mergers, where two galaxies collide and their interstellar gas clouds interact. These collisions can create shock waves that compress gas and dust, leading to a rapid rate of star formation. The study of starbursts triggered by mergers is a fascinating area of research because it can offer clues about the conditions that lead to the formation of the first galaxies after the Big Bang. By studying these processes, we gain insight into the initial stages of galactic evolution and the way that starbursts help build up the chemical elements needed for life. Another avenue for exploring the role of starbursts in galaxy evolution is the study of gas dynamics within starburst regions. Understanding how gas flows in and out of galaxies during starbursts is crucial for grasping how galaxies grow and evolve. Gas inflows, which supply the raw materials for star formation, play a significant role in the development of starbursts. The interaction of gas with the galaxy's central black hole, magnetic fields, and radiation fields can also influence the star formation rate. On the other hand, starbursts can drive gas outflows, powerful galactic winds, that can carry the newly formed stars and elements into intergalactic space. This complex exchange of gas between a galaxy and its environment is a fundamental aspect of galactic evolution, influencing not only the star formation process, but also the chemical enrichment of the universe. The key to understanding these processes lies in the use of cutting-edge observational tools. Telescopes such as the Atacama Large Millimeter/Submillimeter Array, ALMA, the Hubble Space Telescope, and the upcoming James Webb Space Telescope, JWST, offer a level of resolution and sensitivity that allows astronomers to study starbursts in galaxies that are billions of light-years away. These telescopes allow us to detect faint emissions from distant starburst galaxies, enabling the study of their gas content, star formation rates, and the effects of their interactions with neighboring galaxies. One of the exciting prospects of JWST is its ability to observe galaxies as they appeared in the very early universe, providing insight into the first starbursts that occurred shortly after the Big Bang. These observations will help us understand the conditions that led to the formation of the first stars and galaxies, and may offer clues about the processes that shaped the formation of galaxies in the universe's infancy. By studying these ancient starbursts, we can gain a deeper understanding of how galaxies evolve over time, and how the universe has come to be structured as we see it today. Another promising aspect of the study of starbursts is the development of simulations that model the conditions within starburst galaxies. Computational astrophysics has made great strides in simulating the complex interactions that take place within galaxies. These simulations allow astronomers to test different scenarios for the formation of starbursts, and their subsequent effects on galactic evolution. By comparing the predictions made by these simulations with actual observational data, scientists can refine their models and gain a more accurate picture of how starbursts contribute to the larger process of galaxy formation. These models also help astronomers understand the timescales involved in starbursts. Starbursts are not prolonged events. They are often relatively short-lived, lasting only a few million years in a galaxy's lifetime. However, this brief period of intense star formation can have a lasting impact on the galaxy's evolution. Starbursts can transform a galaxy's stellar population, enriching the galaxy with new elements and shaping its overall structure. They can also leave behind evidence of their activity in the form of star clusters, nebulae, and supernova remnants. By studying these remnants, astronomers can piece together the history of a starburst and trace its influence on the galaxy long after the event has subsided. The role of starbursts in the chemical enrichment of galaxies is another area of great interest. During a starburst, new stars form from gas and dust that is enriched by heavier elements produced by older generations of stars. As these new stars age and die, They release these elements into the surrounding gas, further enriching the galaxy's chemical composition. This process is known as stellar nucleosynthesis, and it is one of the primary ways in which galaxies become chemically enriched over time. By studying the chemical composition of starburst galaxies, astronomers can learn about the history of star formation and the buildup of elements in the universe. Understanding how starbursts contribute to the chemical evolution of galaxies is also crucial for understanding the origins of life. The elements produced during star formation, particularly carbon, oxygen, and nitrogen, are the building blocks of life as we know it. By studying the chemical enrichment of galaxies, astronomers can gain insight into the processes that led to the creation of these essential elements and how they were distributed throughout the universe. This knowledge not only helps us understand the evolution of galaxies but also gives us clues about the origins of life on Earth and the possibility of life elsewhere in the universe. As our understanding of starbursts continues to evolve, it will undoubtedly lead to new insights into the broader processes that govern the universe. Starbursts are not just isolated events, they are intricately connected to the larger cosmic fabric. Their influence extends far beyond the confines of individual galaxies, affecting the way galaxies form, grow, and evolve over time. By studying starbursts in greater detail, we can unlock the secrets of galaxy evolution and gain a deeper understanding of the universe's origins and its future. With the continued advancement of technology and our ability to probe deeper into the cosmos, we can look forward to an era of discovery that will bring us closer than ever to understanding the mysteries of starbursts and their role in the grand cosmic narrative. The story of starbursts is far from over, and each new observation brings us one step closer to unraveling the mysteries of the universe. What we discover in the coming decades may change our understanding of how galaxies form and evolve, and it may provide us with answers to some of the most profound questions in astrophysics. As we continue to delve into the mysteries of starbursts and their impact on galactic evolution, it's essential to recognize that these events are more than just episodes of intense star formation. They are integral to the overall process of galaxy transformation, and their study offers a glimpse into the dynamic, ever-changing nature of the universe. The stars born in starburst regions play a key role not only in the evolution of their home galaxies but also in shaping the broader cosmic environment. One fascinating aspect of starbursts is their connection to supermassive black holes, which reside at the centers of most galaxies. These massive black holes are known to have a profound effect on their host galaxies, influencing everything from star formation to galaxy dynamics. In some cases, starbursts and black hole activity are closely linked, with the intense bursts of star formation driving gas toward the central black hole. This process can result in powerful feedback mechanisms that regulate the growth of both the stars and the black hole itself. As a starburst progresses, the immense energy and radiation produced by newly formed stars can heat the surrounding gas, preventing further star formation in certain regions. This feedback process is thought to be one of the factors that determines the size and structure of a galaxy, as well as its eventual fate. In some cases, starbursts can trigger an active galactic nucleus (AGN) phase, during which the black hole at the center of the galaxy becomes extremely active, emitting large amounts of radiation and driving powerful outflows of gas. These AGN-driven outflows, combined with the starburst activity, can significantly alter the dynamics of the galaxy, potentially leading to the quenching of star formation and the eventual transformation of the galaxy into a more passive, red-ended system. The relationship between starbursts and black holes is complex, with different galaxies exhibiting different patterns of interaction. In some galaxies, starbursts and black hole activity occur simultaneously, while in others, one may precede or follow the other. These variations in timing and intensity offer a rich field of study for astronomers, as they seek to understand how these two phenomena are linked and how they shape the evolution of galaxies over time. Moreover, the interplay between starbursts and supernovae, the explosive deaths of massive stars, further complicates our understanding of galactic evolution. Supernovae are a natural outcome of the star formation process, and their shock waves can propagate throughout the galaxy, stirring up the gas and dust that would otherwise have remained undisturbed. These shock waves can trigger new waves of star formation, further fueling the starburst and creating a feedback loop that can last for millions of years. Supernovae also contribute to the chemical enrichment of galaxies, as they release heavy elements into the surrounding space. These elements, such as iron, silicon, and oxygen, are essential for the formation of planets and, by extension, life. As starbursts produce an abundance of these elements, they contribute to the creation of a more diverse and chemically rich environment, setting the stage for the formation of complex systems, including solar systems like our own. The study of supernovae and starburst galaxies, therefore, provides not only insights into the mechanics of stellar death but also a deeper understanding of the chemical building blocks of life. In addition to their connection with supernovae and black holes, starbursts also have an important role in shaping the morphological characteristics of galaxies. While starbursts are often associated with spiral galaxies, they can occur in galaxies of all shapes and sizes, including elliptical and irregular galaxies. The intense star formation associated with starbursts can alter the structure of a galaxy, causing it to become more irregular or distorting its spiral arms. These changes can be temporary, as the starburst eventually subsides and the galaxy returns to a more stable state, but they can also leave lasting marks on the galaxy's morphology, influencing its future development. The morphological transformation of galaxies through starbursts is particularly relevant when considering the fate of galaxies in the distant future. As the universe continues to evolve, galaxies will continue to interact, merge, and undergo various forms of transformation. Starbursts, whether triggered by internal processes or external interactions, will play a pivotal role in this ongoing evolution. By studying starbursts in galaxies at different stages of their life cycles, astronomers can piece together a more complete picture of how galaxies grow, mature, and eventually reach the end of their evolutionary journey. In particular, the study of starbursts in the context of galaxy mergers provides valuable insights into the processes that drive galaxy evolution on the largest scales. When two galaxies collide, their gas clouds interact, triggering intense bursts of star formation. This can lead to the formation of new structures, such as star clusters and stellar tidal tails, as the gravitational forces of the merger distort the galaxy's shapes. Understanding how starbursts evolve in the aftermath of galaxy mergers is crucial for understanding the fate of galaxies in the distant future, as the universe continues to expand and galaxies continue to collide. Moreover, the role of dark matter in these processes cannot be overlooked. While dark matter is invisible to us, its gravitational influence plays a significant role in shaping the structure and evolution of galaxies. Dark matter halos surround most galaxies, providing the necessary gravitational framework for the galaxies to maintain their shape and stability. The interaction between visible matter, gas, stars, and dust, and dark matter during starbursts is an intriguing area of study, as it may reveal new information about the nature of dark matter itself and how it contributes to galactic evolution. The ongoing advancements in technology, such as the development of more powerful telescopes and more sophisticated computational models, will continue to enhance our ability to study starbursts in greater detail. Instruments like the James Webb Space Telescope, the ATACMS, a large millimeter/submillimeter array, and the upcoming Extremely Large Telescope, ELT, will provide unprecedented views of distant starburst galaxies, allowing astronomers to study them with greater precision and accuracy. These observations will help refine our models of galactic evolution and provide new insights into the processes that drive star formation, gas dynamics, and chemical enrichment. In the near future, we may even be able to observe starbursts in galaxies that are still in their infancy, providing a glimpse into the early stages of galaxy formation and evolution. By studying the first generations of stars and galaxies, astronomers can better understand the conditions that led to the formation of the universe's first structures and how the elements necessary for life came to be distributed across the cosmos. The implications of these discoveries are vast. Not only will they enhance our understanding of the universe's history, but they will also contribute to our broader search for life beyond Earth. The elements produced in starbursts and distributed throughout galaxies are the very building blocks of life, and understanding how they came to be is key to understanding how life may arise elsewhere in the universe. As we continue to unravel the mysteries of starbursts, we may find that they are not only essential to the evolution of galaxies but also to the origins of life itself. The future of starburst research is bright, and the discoveries that await us will no doubt change our understanding of the universe in profound ways. As we continue to peer deeper into the cosmos and study the regions of intense star formation, we move closer to unlocking the secrets of galactic evolution and the fundamental processes that govern the universe's growth. The role of starbursts in these processes is undeniable, and the knowledge we gain from studying them will shape our understanding of the cosmos for generations to come. As we continue to explore the significance of starbursts in the broader context of galactic evolution, we encounter another fascinating aspect of these phenomena: their role in the cosmic cycle of matter. When stars are born in a starburst region, they don't just impact the immediate surroundings. They influence the larger environment by enriching the interstellar medium with heavy elements. This process of chemical enrichment is fundamental to the continued evolution of galaxies and the formation of more complex structures, including planets, moons, and potentially life. When massive stars and starburst regions reach the end of their lives, they explode as supernovae, dispersing elements like oxygen, iron, and carbon into the surrounding space. These elements, which were created inside the cores of the stars, are crucial for the formation of new generations of stars and planets. In a sense, starbursts act as cosmic factories, creating and spreading the very elements that are necessary for life as we know it. This cyclical process of star formation, death, and the release of heavy elements helps to perpetuate the formation of new stars and planetary systems, ensuring the ongoing evolution of galaxies. In addition to the chemical enrichment of galaxies, starbursts also play a role in regulating the gas supply available for future star formation. The intense radiation and energy released by newborn stars during a starburst can heat up and ionize the surrounding gas, making it less available for further star formation. This feedback mechanism is essential for preventing a galaxy from undergoing an uncontrollable burst of star formation that could eventually deplete its available gas. In this way, starbursts act as regulators, ensuring that a galaxy's star formation rate remains in balance with the availability of gas. However, the balance between star formation and gas consumption is not always straightforward. In some galaxies, starbursts can lead to a rapid depletion of gas, causing the galaxy to exhaust its fuel for star formation and enter a phase of decline. This is particularly true for galaxies that experience a starburst quenching event, during which the star formation rate dramatically drops after a period of intense activity. Starburst galaxies that undergo quenching may eventually evolve into passive, red-ended galaxies, where star formation has ceased, and the galaxy is dominated by older, low-mass stars. In other cases, starbursts can occur in tandem with the accretion of gas from external sources, allowing the galaxy to replenish its supply of raw material for star formation. This process is particularly common in galaxies that are interacting or merging with other galaxies. The gravitational forces at play during these interactions can funnel gas into the center of the galaxy, where it can fuel the starburst. This ongoing supply of gas helps sustain the star formation process, potentially preventing the galaxy from entering a quiescent state. The interplay between starbursts and galactic interactions is one of the key areas of research in modern astronomy. Galaxy mergers, in particular, are known to trigger intense star formation in the colliding galaxies. When two galaxies collide, their gas clouds collide and compress, leading to a burst of star formation. This burst can occur in both the merging galaxies and in the surrounding regions of the interaction. In some cases, the starburst activity can be so intense that it leads to the formation of a new type of galaxy, known as a starburst galaxy. Starburst galaxies are characterized by their extremely high rates of star formation, often many times greater than that of the Milky Way. These galaxies can be found throughout the universe, from the nearby universe to the distant reaches of the cosmos. The study of starburst galaxies provides valuable insights into the processes that drive galaxy formation and evolution, and they are a key focus of many ongoing astronomical surveys. One of the most intriguing aspects of starbursts in interacting or merging galaxies is the potential for the formation of new and exotic types of stellar objects. During a starburst, the extreme conditions can lead to the formation of massive, short-lived stars that burn through their fuel at an incredible rate. These stars, known as Wolf-Rayet stars, are some of the most massive stars in the universe and are thought to be the precursors to supernovae. The study of Wolf-Rayet stars and starburst galaxies is an exciting area of research, as it offers clues about the end stages of stellar evolution and the role of massive stars in galactic evolution. In addition to their role in star formation and chemical enrichment, starbursts also influence the overall dynamics of galaxies. The gravitational forces exerted by the dense concentration of stars and gas in starburst regions can cause significant changes in the motion of stars and gas throughout the galaxy. These changes can lead to the formation of new structures, such as spiral arms, bars, and rings, as the galaxy responds to the intense activity in its core. In some cases, starbursts can even trigger the formation of a new galaxy structure altogether, leading to the creation of irregular or distorted galaxies. The influence of starbursts on galaxy dynamics is particularly evident in the case of interacting galaxies. When two galaxies collide, the gravitational forces between them can distort their shapes, creating tidal tails, bridges, and other structures. These interactions can lead to the formation of new stars and star clusters, as well as the redistribution of gas and dust throughout the galaxy. The resulting starburst activity can further enhance the already dramatic changes in the galaxy's structure, leading to the creation of new, often unpredictable, forms of galactic morphology. In the larger cosmic picture, starbursts provide essential clues about the conditions that led to the formation of the first galaxies in the universe. By studying the most distant starburst galaxies, astronomers can gain insights into the earliest stages of galaxy formation, when the first stars and galaxies were beginning to take shape. These observations also shed light on the processes that govern the growth of supermassive black holes, which are thought to have played a key role in shaping the evolution of galaxies during the cosmic dawn. The ongoing study of starbursts and their impact on galactic evolution is expected to yield even more groundbreaking discoveries in the coming years. With the advent of new observational tools, such as the James Webb Space Telescope and the Extremely Large Telescope, astronomers will be able to probe deeper into the universe and study the most distant and faintest starburst galaxies. These observations will provide critical insights into the processes that drive the formation and evolution of galaxies and help answer some of the most fundamental questions about the nature of the universe itself. As we look to the future of starburst research, we can anticipate the continued development of more sophisticated models and simulations that will allow us to better understand the complex interactions between star formation, gas dynamics, and galaxy morphology. By integrating observations with theoretical models, astronomers will be able to paint a more complete picture of how starbursts shape the evolution of galaxies and contribute to the broader cosmic cycle of matter. Ultimately, starbursts represent a crucial piece of the puzzle in our quest to understand the nature of the universe. They are the engines of galaxy evolution, driving the formation of stars, the enrichment of interstellar space, and the transformation of galaxies into the diverse structures we observe today. As we continue to study these dynamic, explosive events, we will uncover even more secrets about the cosmos and the forces that have shaped it over billions of years. The role of starbursts in galactic evolution is far from fully understood, and their mysteries continue to captivate scientists. As we continue to delve deeper into the fascinating role of starbursts in galactic evolution, one area that warrants further exploration is the relationship between starbursts and the formation of supermassive black holes. These enigmatic objects, which reside at the centers of most large galaxies, are thought to play a crucial role in the growth and evolution of galaxies. The interaction between starbursts and supermassive black holes is a subject of intense research, as it may provide key insights into how galaxies grow, evolve, and regulate their star formation over time. The link between starbursts and supermassive black holes comes into focus when we consider the effects of intense star formation on the central regions of galaxies. In starburst galaxies, the concentration of gas and stars in the core can trigger the accretion of material onto a supermassive black hole. This process, known as active galactic nucleus (AGN) activity, is often associated with the release of enormous amounts of energy, which can have significant consequences for the surrounding galaxy. As gas falls toward the supermassive black hole, it forms a hot, dense accretion disk that radiates energy across the electromagnetic spectrum, from X-rays to radio waves. The energy emitted by the accretion disk can have a profound impact on the surrounding gas and stars, heating up the interstellar medium and potentially suppressing further star formation. This feedback mechanism, known as AGN feedback, is thought to play a critical role in regulating the growth of galaxies and preventing them from becoming overactive in terms of star formation. Interestingly, the activity of supermassive black holes and starburst galaxies is not one-sided. While the supermassive black hole can influence its surrounding environment through AGN feedback, the intense star formation occurring in the galaxy's core can also feed material into the black hole, creating a cycle of growth and feedback. This mutual relationship between starbursts and supermassive black holes suggests that the two phenomena may be intricately linked, with each influencing the other's evolution. In some cases, the feedback from an active supermassive black hole can halt or even reverse the starburst process. The powerful radiation and outflows from the AGN can expel gas from the central regions of the galaxy, disrupting the conditions needed for star formation. This process, known as starburst quenching, has been observed in many galaxies, where the once active starburst region fades as the black hole's activity suppresses further star formation. The interplay between starbursts and supermassive black holes, therefore, represents a delicate balance, with the potential to shape the long-term evolution of galaxies. The role of starbursts in fueling supermassive black holes also raises intriguing questions about the growth of these objects over cosmic time. It is believed that the earliest galaxies, which formed shortly after the Big Bang, may have undergone rapid periods of star formation and black hole growth. In these primordial galaxies, starbursts and supermassive black holes could have played a symbiotic role in driving the evolution of the galaxy and its central black hole. Studying distant starburst galaxies and their associated supermassive black holes may help astronomers understand the conditions that led to the formation of the first massive galaxies and black holes, offering a glimpse into the cosmic dawn. Moving beyond the role of supermassive black holes, another intriguing aspect of starbursts is their connection to the large-scale structure of the universe. While starbursts are often associated with individual galaxies, they also have the potential to influence the larger cosmic environment in which galaxies reside. For example, starburst galaxies that are part of galaxy clusters may contribute to the overall dynamics of the cluster, affecting the behavior of other galaxies and the distribution of matter within the cluster. In galaxy clusters, the interaction between starburst galaxies and their neighbors can lead to a variety of interesting phenomena. For instance, the strong gravitational forces within a cluster can cause galaxy collisions and mergers, which can trigger starbursts. The resulting burst of star formation can significantly alter the appearance and properties of the galaxies involved, potentially transforming a relatively passive galaxy into a starburst galaxy. Moreover, the energetic outflows from starburst galaxies can interact with the hot gas that pervades galaxy clusters, influencing the cluster's overall thermal and dynamical properties. The influence of starbursts on the large-scale structure of the universe extends beyond galaxy clusters. When we look at the distribution of galaxies across the cosmos, we see that starbursts are more common in certain regions, such as in the centers of galaxy groups or in the early universe. Understanding the role of starbursts in these different environments can provide valuable insights into how galaxies evolve within the larger framework of cosmic structures. For instance, starburst activity may play a role in the formation of galaxy groups or the buildup of large-scale cosmic filaments. By studying how starbursts interact with their environments, astronomers can better understand the processes that drive the formation and growth of galaxies on the largest scales. One of the most exciting aspects of starbursts is their potential to provide clues about the early universe. As we observe distant galaxies, we are effectively looking back in time, witnessing the birth and evolution of galaxies as they appeared billions of years ago. Many of the most distant galaxies we observe are undergoing intense starbursts, indicating that these regions of rapid star formation played a key role in the formation of galaxies during the early stages of cosmic history. In fact, some of the most distant starburst galaxies ever discovered have been observed by the Hubble Space Telescope and other observatories. These galaxies, which are seen as they were just a few 100 million years after the Big Bang, provide a glimpse into the conditions that existed during the epoch of reionization. This period, which occurred between 500 million and 1 billion years after the Big Bang, marked the end of the cosmic dark ages and the beginning of the universe's transition to the state we observe today. The study of starbursts in these distant galaxies offers valuable insights into the processes that occurred during this critical period of cosmic history. Furthermore, the discovery of population 3 stars, the first generation of stars to form after the Big Bang, has revolutionized our understanding of starbursts in the early universe. These stars were composed almost entirely of hydrogen and helium, the primordial elements created during the Big Bang. They were likely much more massive than the stars we observe today, and would have played a key role in the formation of the first galaxies and the initiation of starbursts. While population 3 stars have not yet been directly observed, their presence is inferred from the study of distant starburst galaxies and the chemical composition of the intergalactic medium. The role of starbursts in the early universe highlights their importance in shaping the large-scale structure of the cosmos. These intense episodes of star formation were not only responsible for creating the first stars and galaxies, but they also contributed to the reionization of the universe, a process that set the stage for the formation of more complex structures, such as galaxy clusters and cosmic filaments. Starbursts, in this sense, represent a pivotal moment in the history of the universe, one that continues to shape the cosmos to this day. As we move forward in our exploration of starbursts and their role in galactic evolution, it becomes clear that these phenomena are far more than just brief, explosive bursts of star formation. They are integral to the ongoing process of galaxy formation, the chemical enrichment of the universe, and the larger-scale evolution of cosmic structures. By studying starbursts in detail, we gain not only a deeper understanding of how galaxies evolve, but also a broader appreciation for the complex and interconnected nature of the universe itself. Starbursts also play a significant role in the chemical enrichment of the universe, and this aspect is critical to understanding how elements heavier than hydrogen and helium, known as metals, in astronomical terms, came to be distributed throughout galaxies. These metals are essential for the formation of planets, stars, and even life as we know it. During a starburst, the intense rate of star formation leads to the rapid production of new stars, some of which are massive enough to end their lives in supernovae, explosive deaths that release vast quantities of metals into the surrounding interstellar medium. These supernovae are responsible for producing and dispersing the elements that form planets, life, and the next generation of stars. The process of chemical enrichment in starburst galaxies is closely tied to the stages of stellar evolution. As massive stars form and reach the end of their lives, they undergo violent supernova explosions, scattering heavier elements such as carbon, oxygen, and iron throughout their host galaxy. This enrichment process is not limited to just one generation of stars. The metals released by these supernovae mix with the interstellar gas, and when new stars form from this enriched gas, they contain a higher proportion of heavier elements. This cyclical process of star formation and supernovae continues, gradually increasing the metal content of a galaxy and influencing its overall composition and evolution. Interestingly, the rate of chemical enrichment in starburst galaxies can be much higher than in galaxies with more moderate star formation rates. This is due to the high volume of new stars being formed in a relatively short period. In some cases, the chemical enrichment from starbursts can lead to a rapid increase in the metallicity of a galaxy, significantly altering its stellar population and the types of stars that can form. The presence of metals is also a key factor in the cooling of gas within galaxies, as the heavier elements allow the gas to radiate away heat more efficiently. This cooling effect is crucial for the formation of dense molecular clouds, where new stars are born. The high rates of star formation and chemical enrichment in starburst galaxies also have important implications for the broader cosmic environment. The outflows of gas and metals from starburst regions can be transported across vast distances, enriching the intergalactic medium and influencing the evolution of other galaxies. These outflows, driven by the pressure from supernovae, stellar winds, and sometimes the activity of an active supermassive black hole, can carry metals far beyond their host galaxy, spreading the chemical products of star formation throughout the universe. This enrichment of the intergalactic medium is thought to have been a significant factor in the overall chemical evolution of the universe. In the early stages of cosmic history, the universe was primarily composed of hydrogen and helium, with only trace amounts of heavier elements. Over time, starbursts and the subsequent release of metals from dying stars helped to enrich the gas between galaxies, eventually leading to the creation of more complex structures and the conditions necessary for the formation of planets and life. Starbursts, by facilitating the rapid production and distribution of metals, also contribute to the diversity of galaxies we see today. The chemical composition of a galaxy plays a major role in determining its properties, including its ability to form new stars, the types of stars that can form, and the potential for the development of planets. By studying the chemical enrichment of starburst galaxies, astronomers can gain insights into the processes that led to the creation of the diverse range of galaxies in the universe, from the small, metal-poor dwarf galaxies to the massive, metal-rich spiral galaxies. The study of starbursts and their impact on galactic evolution also provides valuable information about the different types of galaxies we observe in the universe. While starbursts are most commonly associated with irregular galaxies or those in the process of merging, they can also occur in more evolved galaxies, including spiral galaxies. The Milky Way, for example, has experienced several periods of intense star formation over its lifetime, though these bursts of activity were typically less extreme than those seen in starburst galaxies. In some cases, starbursts can even be triggered by external factors, such as interactions with neighboring galaxies. When galaxies collide or pass close to one another, the gravitational forces involved can cause gas to compress, triggering a burst of star formation. This phenomenon is observed in interacting or merging galaxies, where the gas in the interstellar medium is disturbed by the interaction, leading to the rapid formation of new stars. These tidal starbursts provide additional evidence of how galactic interactions can influence star formation and contribute to the overall evolution of galaxies. Looking at the broader picture, starbursts are an essential part of the process that shapes the life cycle of galaxies. They represent a period of intense activity and transformation, during which galaxies undergo dramatic changes. The birth of new stars, the formation of supernovae, the release of metals into the interstellar medium, and the potential for the triggering of supermassive black hole activity all contribute to the dynamic nature of starburst galaxies. By studying these galaxies, astronomers can learn not only about the specific events occurring within individual galaxies but also about the larger processes that govern the formation and evolution of galaxies across the universe. The study of starbursts is also closely tied to the ongoing search for answers to some of the most fundamental questions in cosmology. For example, understanding how starbursts contribute to the formation of galaxies can help us understand the conditions that led to the first galaxies and stars in the early universe. Observing distant starburst galaxies allows astronomers to peer back in time and witness the rapid star formation that took place during the epoch of reionization. This, in turn, provides crucial clues about the processes that shaped the universe during its earliest stages. As we continue to explore the role of starbursts in galactic evolution, we also begin to appreciate the complex interactions between galaxies, stars, gas, and dark matter. The dynamics of starbursts are influenced by many factors, including the large-scale structure of the universe, the availability of gas for star formation, the presence of supermassive black holes, and the interactions between galaxies. These factors work together to shape the evolution of galaxies, leading to the rich diversity of galaxy types and structures we observe today. In the future, as new telescopes and instruments come online, we will continue to expand our understanding of starbursts and their role in the universe. The James Webb Space Telescope, for example, is expected to provide unprecedented insights into the distant, high-redshift starburst galaxies that formed in the early universe. With its ability to observe in the infrared, Webb will be able to detect the faint, redshifted light from these galaxies, allowing astronomers to study the star formation processes that occurred billions of years ago. Starbursts are much more than just temporary bursts of star formation. They are a fundamental driver of galactic evolution. By studying starbursts, we gain valuable insights into the processes that shape galaxies, from the production of stars and metals to the triggering of supermassive black holes, and the enrichment of the intergalactic medium. These intense periods of star formation offer a glimpse into the dynamic and ever-changing nature of the universe, helping us to understand the forces that have shaped galaxies over cosmic time. Through ongoing research and observation, we will continue to uncover the mysteries of starbursts, adding to our understanding of the universe and our place within it. As we move forward in our study of starbursts, it's important to recognize the diverse environments in which they occur and the potential impact these environments have on the star formation process. Starbursts are not one-size-fits-all phenomena. They can vary greatly depending on factors such as the size, mass, and structure of the host galaxy, as well as the specific conditions within those galaxies. For example, while starbursts in smaller, irregular galaxies are often fueled by the gravitational interactions of nearby galaxies, in larger galaxies, starbursts may be triggered by internal processes such as the collapse of dense molecular clouds or by an active galactic nucleus. One particularly interesting environment in which starbursts are found is in the centers of galaxies that harbor active supermassive black holes. These central black holes can exert a tremendous amount of gravitational influence on their surroundings, often leading to the formation of vast gas disks that spiral inward toward the black hole. In some cases, this accumulation of gas can trigger starbursts in the surrounding regions. The energy released by the black hole, whether through radiation or powerful jets of gas, can further influence star formation by compressing gas clouds and triggering bursts of star formation in the galaxy's central regions. On the other hand, starbursts can also be triggered by external forces. The most common of these forces are galactic interactions, such as mergers and close encounters. When galaxies collide, their gas and dust clouds are compressed, causing bursts of star formation. These galactic collisions, particularly those between gas-rich galaxies, can lead to the formation of new stars in a short period of time. The resulting starburst can dramatically change the morphology of the galaxies involved, sometimes even transforming them from spiral galaxies into elliptical galaxies as the gas is exhausted or ejected, leaving behind a remnant population of stars. Another type of starburst occurs in environments where gas is funneled into the center of a galaxy. This often happens in galaxies with a high rate of gas accretion, which might be driven by interactions with a nearby galaxy, or through the gravitational pull of a supermassive black hole. As the gas funnels inward, it can ignite star formation in the galaxy's center, where the conditions are ripe for new stars to form. The central starburst, in turn, can dramatically affect the evolution of the galaxy as a whole by influencing the dynamics of the gas and the formation of new stars in the surrounding regions. While the exact mechanisms behind starbursts can be complex, it is clear that they play an essential role in shaping the evolution of galaxies. The creation of new stars, the release of metals into the interstellar medium, and the eventual formation of supernovae all contribute to the evolution of galaxies and their environments. By studying starbursts, we gain insight into the processes that govern the growth and transformation of galaxies, from the early stages of star formation to the eventual formation of galactic structures like spiral arms or elliptical cores. One of the key questions that astronomers are still trying to answer is how starbursts relate to the overall star formation rate of a galaxy. Some galaxies experience continuous, steady star formation over long periods of time, while others undergo intense bursts of star formation. Understanding the balance between these two modes of star formation is crucial for understanding the long-term evolution of galaxies. It is possible that galaxies that experience starbursts may have higher rates of stellar birth in their early stages but lower rates of star formation in their later stages, as the gas needed to form new stars gets depleted. Starbursts also have a significant impact on the surrounding environment, particularly in terms of their influence on the intergalactic medium. When starbursts occur, they often generate powerful winds and outflows of gas that can carry metals and energy away from the galaxy. These outflows can enrich the surrounding intergalactic space with heavy elements, helping to spread the materials necessary for the formation of new galaxies, stars, and even planets. This process, known as feedback, is thought to play an important role in regulating the growth of galaxies and preventing them from becoming too massive. It is likely that starbursts, through their outflows, help to shape the large-scale structure of the universe by distributing material across vast distances. The connection between starbursts and feedback is also seen in the way that starbursts can influence the formation of supermassive black holes. As the starburst fuels intense star formation in the galaxy's center, it can lead to the accumulation of gas and dust in the central regions, which may eventually be drawn into the supermassive black hole. This accretion of gas can power active galactic nuclei, AGN, which can release large amounts of energy in the form of radiation and jets. The energy from these AGN can, in turn, influence the surrounding galaxy, inhibiting further star formation by heating the gas and preventing it from cooling and condensing into new stars. In addition to this, starbursts are closely linked to the concept of galaxy morphology. The shape and structure of galaxies are determined by a variety of factors, including the rate of star formation, the presence of a supermassive black hole, and the amount of gas available for star formation. Starbursts can dramatically alter a galaxy's morphology by rapidly creating new stars and ejecting gas. In some cases, these processes can transform a galaxy from a spiral or irregular shape into an elliptical galaxy, with a large population of older stars and little gas remaining for further star formation. In other cases, starbursts can create new spiral arms, leaving behind a more complex structure with a higher rate of star formation. The study of starbursts also has important implications for our understanding of the early universe. Observing distant starbursts allows astronomers to study the conditions that led to the formation of the first galaxies and stars in the aftermath of the Big Bang. By studying these starburst galaxies, astronomers can gain insight into the processes that occurred during the early stages of cosmic evolution and help to answer some of the most fundamental questions in cosmology. How did galaxies form in the first place? What were the conditions that led to the creation of the first stars? How did the universe transition from a state dominated by gas to one where galaxies and stars could form? Starbursts offer a unique window into this critical period of cosmic history. Looking ahead, the study of starbursts will continue to be a key area of research in the field of astronomy. As new telescopes and instruments come online, astronomers will have even more powerful tools at their disposal to study these enigmatic regions of intense star formation. The James Webb Space Telescope, for example, will provide unprecedented observations of starbursts in the distant universe, allowing scientists to study the star formation processes that took place billions of years ago. With its advanced infrared capabilities, Webb will be able to peer through the dust and gas surrounding starbursts, giving us a clearer view of the stars and galaxies in the process of formation. Starbursts are a crucial aspect of galactic evolution, contributing to the formation of new stars, the enrichment of the interstellar medium, and the shaping of galactic structures. By studying starbursts, we gain valuable insights into the processes that drive the evolution of galaxies and the larger universe. Whether triggered by internal factors, such as gas accumulation or supermassive black hole activity, or external factors, such as galactic mergers and interactions, starbursts offer a fascinating glimpse into the dynamic and ever-changing nature of the cosmos. As our understanding of these phenomena continues to grow, we will continue to uncover new insights into the workings of the universe, deepening our appreciation for the intricate processes that govern the birth and evolution of galaxies. Starbursts not only affect the evolution of galaxies, but they also play a pivotal role in the broader context of the universe's evolution. Understanding the life cycles of starbursts is integral to understanding how galaxies grow and evolve over cosmic time. When a galaxy undergoes a starburst, it experiences rapid star formation, often far outpacing the typical rate observed in normal galaxies. This burst of activity can significantly alter the galaxy's stellar population, leading to the creation of a wide variety of stars, from massive, short-lived stars to more moderate, longer-living ones. The intense radiation and energetic events produced by these stars, particularly when they reach the end of their lives in supernova explosions, also have profound effects on the surrounding environment. These supernovae, in particular, contribute to the enrichment of the galaxy's interstellar medium, ISM. As massive stars reach the end of their life cycles and explode in violent supernovae, they release heavy elements like carbon, oxygen, and iron into the surrounding gas. These elements are crucial for the formation of future generations of stars, planets, and potentially life itself. Without these supernovae, the universe would lack the essential building blocks for the formation of more complex structures. The heavy elements released during starbursts are scattered into the ISM, where they can later be incorporated into new stars and planetary systems, playing a vital role in the chemical evolution of galaxies. However, the process is not without consequences. The energy released during a starburst, particularly from supernovae and stellar winds, can trigger the expulsion of gas from the galaxy. This outflow of material, often termed a galactic wind, can deplete the galaxy of its gas, thereby halting further star formation. This cycle of star formation followed by gas depletion is a critical factor in regulating the long-term evolution of galaxies. As galaxies run out of the raw materials necessary for star formation, they may transition from being star-forming, active systems to passively aging systems with little new star formation. In addition to this, the feedback mechanisms initiated by starbursts can also influence the galaxy's dark matter halo. Dark matter, which is thought to make up the majority of a galaxy's mass, exerts a gravitational influence that affects the motion of visible matter within the galaxy. In galaxies experiencing intense star formation, the energetic feedback from the stars and supernovae may influence the behavior of the dark matter halo, potentially altering the galaxy's rotation curve or its overall structure. This suggests that starbursts may not only be shaping the visible components of galaxies, but may also have an impact on the unseen, mysterious dark matter that dominates the mass of most galaxies. Furthermore, the role of starbursts in galaxy evolution extends to the question of whether they could lead to the formation of different types of galaxies. For instance, as a starburst progresses, it may lead to the creation of an elliptical galaxy if the gas is exhausted or blown away. Elliptical galaxies, in contrast to the more familiar spiral galaxies, are typically characterized by a lack of interstellar gas and a population of older stars. Thus, while starbursts initially fuel rapid star formation, their aftermath can lead to the creation of galaxies that are no longer able to form stars efficiently. In this sense, starbursts represent a critical stage in a galaxy's life cycle, one that can have profound implications for the long-term future of that galaxy. Moreover, starbursts do not occur in isolation. They are often linked with other cosmic phenomena such as AGN, active galactic nuclei, and cosmic inflows of gas. As previously mentioned, AGN activity, which often occurs in the center of galaxies, can drive significant changes in the surrounding star-forming regions. The central black holes of galaxies can influence the starbursts by heating or ejecting gas, altering the environment in which stars are born. In some cases, the presence of an AGN can suppress star formation by expelling gas from the galaxy or by heating the surrounding interstellar medium, preventing gas clouds from collapsing and forming new stars. At the same time, galaxies undergoing starbursts can also experience cosmic inflows of gas, sometimes referred to as cosmic rain. These gas clouds, often originating from the surrounding cosmic environment, can fuel star formation by replenishing the galaxy's gas reserves. This influx of gas can extend the duration of a starburst, or even trigger a second wave of star formation in galaxies that might otherwise have exhausted their resources. In this way, starbursts can be sustained by a dynamic balance between the outflows of gas, due to supernovae and AGN activity, and the inflows of new material from the intergalactic medium. As we observe starbursts in the distant universe, we can also gain insights into the conditions of the early universe. The first generations of stars, formed shortly after the Big Bang, were likely born in environments similar to the intense star-forming regions we see today. By studying the starburst galaxies that existed when the universe was young, astronomers can learn more about the conditions that led to the formation of the first galaxies and stars. The starburst phenomena we observe today may, in fact, be echoes of the processes that governed the very early stages of cosmic history. One of the key tools that astronomers use to study starbursts is their ability to observe galaxies in different wavelengths of light. While visible light provides important information about the stars themselves, other wavelengths, such as infrared, allow us to peer through the dust and gas that often obscure our view of the heart of these star-forming regions. In particular, the James Webb Space Telescope, with its advanced infrared capabilities, is expected to offer unprecedented insights into the processes that govern starbursts in distant galaxies. This will provide astronomers with an invaluable opportunity to observe star formation in galaxies that are billions of light-years away, offering a glimpse into the past and allowing us to trace the evolution of galaxies over cosmic time. Looking forward, there is still much to learn about the complex relationship between starbursts and the evolution of galaxies. While we have made great strides in understanding the processes that drive star formation, we still lack a complete understanding of how starbursts influence the overall dynamics of galaxies and the broader universe. Future observations, particularly those made with next-generation telescopes and observatories, will help to fill in the gaps in our knowledge and reveal new insights into the role that starbursts play in shaping the galaxies and structures that populate the cosmos. Starbursts are one of the most fascinating and crucial phenomena in the study of galaxy evolution. These intense bursts of star formation shape the dynamics, chemistry, and structure of galaxies in profound ways. Through the processes of star formation, supernovae, and feedback, starbursts contribute to the enrichment of the interstellar medium, the evolution of galaxy morphology, and the overall growth of galaxies. While the precise mechanisms behind starbursts are still being studied, it is clear that they play a vital role in shaping the universe we observe today. As our understanding of these processes deepens, we will continue to unravel the mysteries of star formation and the evolution of galaxies, gaining insights into the very nature of the cosmos itself. As we continue to explore the mysteries surrounding starbursts and their crucial role in galactic evolution, it becomes evident that starbursts are not just isolated events, but rather, they represent dynamic, intricate phases in the life of a galaxy. The interplay between star formation, feedback mechanisms, gas exchange, and the surrounding environment reveals a much deeper, interconnected story. This intricate balance shapes galaxies and influences the larger cosmic framework in ways that extend far beyond the immediate environment of a single starburst event. One of the most compelling aspects of starbursts is their connection to the growth of supermassive black holes at the centers of galaxies. Supermassive black holes, often thought to be present in the cores of nearly all large galaxies, play a key role in shaping the evolution of their host galaxies. During a starburst, the increased rate of star formation can significantly affect the dynamics of the galaxy's core, particularly the availability of gas that may ultimately feed the supermassive black hole. These energetic feedback loops are not just passive, but actively shape the galaxy. When massive stars end their lives in explosive supernovae, they not only enrich the galaxy's ISM with heavy elements, but their death also releases an enormous amount of energy. This energy, in turn, can trigger the central black hole to increase its activity, feeding it with gas and enhancing its growth. A more active black hole can release massive amounts of radiation, which can, paradoxically, suppress star formation in the surrounding galaxy by heating and dispersing the gas, halting the star-forming process. This feedback mechanism, which links star formation with black hole growth, is one of the most important factors in understanding how galaxies evolve. Starbursts also act as a cosmic clock, offering astronomers a snapshot of galaxy evolution at different stages in the universe's history. The study of starburst galaxies, particularly those in the distant universe, provides insights into the conditions that led to the formation of galaxies in the early cosmos. By observing how galaxies in different cosmic epochs experience bursts of star formation, astronomers can deduce the conditions that existed in the early universe, such as the availability of gas and the conditions under which stars first formed. This allows us to trace the timeline of galactic evolution and gain a deeper understanding of the mechanisms that governed the early growth of galaxies, providing clues about the origins of cosmic structures. One of the intriguing aspects of starbursts is their occurrence in different environments. While starbursts are typically associated with specific regions, such as interacting galaxies or galaxy mergers, they can also be found in seemingly isolated galaxies. In some cases, starbursts can be triggered by internal factors, such as gravitational instabilities or the sudden influx of gas. In others, external factors, such as interactions with neighboring galaxies, can trigger a burst of star formation. This diversity of triggers suggests that starbursts are not a singular phenomenon, but rather a response to a variety of different cosmic events and environmental conditions. The study of these different types of starbursts, whether triggered by internal instability, galactic collisions, or other external forces, provides valuable insights into the conditions that foster rapid star formation. It also raises intriguing questions about the future evolution of these galaxies. Are they doomed to a brief period of intense star formation before entering a passive, aging phase? Or is there potential for these galaxies to continue forming stars at a steady pace, evolving into long-lived systems with rich stellar populations? These questions remain open, and future observations and studies will help to shed light on the long-term fate of starburst galaxies. When looking at the long-term consequences of starbursts, it is essential to consider their impact on the chemical evolution of galaxies. Starbursts not only provide the conditions for the creation of new stars, but they also contribute to the galaxy's chemical makeup. As stars form and evolve, they produce elements like hydrogen, helium, oxygen, and carbon, and release them into the surrounding interstellar medium. This process, known as chemical enrichment, ensures that galaxies become more complex over time, with increasing concentrations of heavier elements. Starbursts, through their rapid pace of star formation, act as accelerators of this chemical enrichment. Massive stars that form during a starburst phase live fast and die young, releasing large amounts of heavy elements during their supernova explosions. These elements, such as iron and nickel, are vital for the formation of planets, and their dispersal into the ISM creates the building blocks for future generations of stars and planetary systems. The feedback from starbursts not only enriches the chemical composition of the galaxy, but also influences the types of stars and planetary systems that can form in the future. Beyond their chemical impact, starbursts can also serve as important indicators of a galaxy's age and its evolutionary stage. A galaxy undergoing a starburst may be experiencing a period of rapid transformation, possibly as a result of a merger, an inflow of gas, or other cosmic events. The intensity of star formation during this phase can give clues about the overall age of the galaxy and the types of events that led to its current state. These age indicators can also be combined with other observables to place galaxies within a broader cosmological context. For example, starbursts in galaxies that are billions of light-years away represent a snapshot of the universe during a particular period of its evolution, offering us a glimpse into the conditions that led to the formation of galaxies in the early universe. By studying these distant starburst galaxies, astronomers can test theories about galaxy formation, the role of dark matter, and the fundamental processes that have shaped the evolution of cosmic structures. At the heart of starburst research is the concept of galaxy morphology, the shape and structure of galaxies, which provide important clues about their evolution. Starbursts can play a critical role in the transformation of a galaxy's morphology. For instance, when a galaxy experiences a starburst triggered by a merger or interaction, its shape can change dramatically. The intense gravitational forces at play during a collision can distort the galaxy's structure, leading to the formation of new features, such as tidal tails, bars, or rings of star formation. These morphological changes can have profound implications for the galaxy's future, influencing its star formation rate, its gas content, and its overall stability. Starbursts, particularly in the context of galaxy mergers, also contribute to the formation of elliptical galaxies. When two gas-rich spiral galaxies collide and merge, the resulting starburst can rapidly consume the available gas, leading to a depletion of star-forming material. This process can transform the galaxy from a star-forming spiral into a passively evolving elliptical galaxy, which is characterized by a more stable stellar population and minimal ongoing star formation. This transformation offers insight into the long-term fates of galaxies, and how starbursts can contribute to the diversity of galaxy types in the universe. As we continue to study the phenomena of starbursts, we also learn about the broader cosmic cycles of matter. The enrichment of the ISM through the release of heavy elements during starbursts is a crucial component of the cosmic recycling process. This process, which involves the creation and destruction of stars and galaxies, ensures that the universe continues to evolve and that new generations of stars and planetary systems are born from the remains of older ones. Starbursts, through their intense bursts of star formation and their dramatic effects on galaxy dynamics, are one of the most direct ways that matter is recycled in the cosmos. Starbursts are not simply short-lived bursts of activity within galaxies, but rather, they represent essential phases in the ongoing evolution of the universe. These events shape the structure, chemical composition, and future of galaxies, while providing us with key insights into the history of the cosmos. By studying starbursts, astronomers gain a deeper understanding of how galaxies form, grow, and evolve, and how they interact with the larger cosmic environment. The continued study of these phenomena will reveal even more about the intricate and dynamic processes that govern the universe and help to answer some of the most profound questions about the origins and evolution of cosmic structures. As technology advances and our observational capabilities improve, the mystery surrounding starbursts will continue to unfold, offering new insights into the cosmos and its evolution. As we continue to unravel the mysteries of starbursts and their profound influence on galactic evolution, we begin to see a clearer picture of how these energetic phenomena contribute to shaping the universe in both the short and long term. Starbursts are not only critical to the evolution of individual galaxies, but they also play a significant role in the broader cosmic narrative. Their impact can be seen not only in the galaxies themselves but also in the larger-scale structures that make up the cosmos. One of the most striking aspects of starbursts is their ability to reshape the environments in which they occur. A region of intense star formation can generate powerful winds and outflows of gas, driven by the radiation pressure from newly formed stars, the energy released by supernovae, and the active feedback from supermassive black holes. These outflows of gas have a far-reaching effect on the galaxy's surrounding medium, often expelling material out of the galaxy and contributing to the larger-scale dynamics of the intergalactic medium, IGM. The ejected gas, rich in heavy elements produced by stars, can become part of the intergalactic gas clouds that permeate the space between galaxies. This process, known as galactic feedback, plays an important role in regulating the growth of galaxies and the overall chemical enrichment of the universe. As gas is expelled from a galaxy during a starburst, it may eventually return, either through processes like galactic winds or by gravitational pull from neighboring galaxies, enriching other parts of the universe with heavy elements and triggering future generations of star formation. This ongoing cycle of material movement contributes to the overall cosmic evolution, influencing the composition of galaxies, the formation of new stars, and the complex interplay between galaxies and clusters. In this way, starbursts serve as both catalysts and regulators of galactic evolution. The initial burst of star formation can trigger the creation of new stars, while also setting in motion a feedback loop that regulates the rate of star formation over time. As gas is consumed in the starburst, it becomes increasingly difficult for the galaxy to sustain such high levels of star formation. At some point, the galaxy may experience a decline in star formation, either due to the depletion of its gas reserves or due to the effects of feedback processes like supernovae or black hole activity. This decline can mark the transition from a star-forming phase to a more passive, quiescent state, often associated with the transition from a spiral galaxy to an elliptical one. The influence of starbursts on galaxy morphology is particularly interesting because it highlights the complex relationship between star formation, galaxy shape, and the underlying physics of the universe. As starbursts can trigger galaxy mergers and interactions, they can also lead to the formation of peculiar galaxy shapes, such as ring galaxies, mergers with tidal tails, or galaxies with elongated structures. These morphological transformations offer valuable clues about the history of a galaxy and its interactions with its environment. Understanding these changes is crucial to gaining a comprehensive understanding of galactic evolution, as galaxy morphology is often tied to a galaxy's stellar population, gas content, and overall activity. Starbursts also contribute to the ongoing growth of galactic structures, particularly the halos that surround galaxies. These halos, composed of dark matter and gas, are fundamental to the gravitational binding of galaxies and their long-term evolution. The energy released during a starburst can impact the dynamics of these halos, influencing how matter is distributed and how galaxies interact with each other over cosmic timescales. By studying how starbursts affect these halos, astronomers can learn more about the role of dark matter in galaxy formation and the forces that govern the structure of the universe. The study of starbursts extends beyond the local universe, reaching into the depths of distant galaxies and providing a glimpse into the early cosmos. Starbursts are often observed in distant galaxies, where the light from these energetic events takes millions or even billions of years to reach us. These distant starbursts offer a unique opportunity to study the conditions that prevailed in the early universe, allowing astronomers to investigate the formation of the first galaxies, the buildup of heavy elements, and the evolution of cosmic structures. By studying these distant starbursts, we can better understand how the first stars and galaxies formed and evolved in the early stages of the universe. The role of starbursts in galaxy evolution also ties into the broader questions of cosmic inflation, the formation of large-scale structures, and the fundamental processes that govern the universe. In particular, starbursts contribute to the ongoing enrichment of the universe by providing the building blocks for future generations of stars, planets, and life. The elements produced during star formation, such as carbon, oxygen, and nitrogen, are essential for the creation of life as we know it. These elements are dispersed throughout the galaxy, enriching the interstellar medium and providing the raw materials for future generations of stars and planetary systems. In this way, starbursts are not just about the birth of stars, but also about the creation of the elements that make life possible. The ongoing study of starbursts and their role in galactic evolution promises to continue yielding new insights into the universe's history and its future. As astronomers develop more advanced observational techniques and gather more data on distant galaxies, they will be able to study starbursts in greater detail, uncovering the mechanisms that drive these phenomena and how they shape the galaxies in which they occur. In particular, the study of starbursts in the early universe, through observations of high-redshift galaxies, will provide key insights into the processes that governed the formation of the first galaxies and the conditions that allowed for the emergence of complex structures. Furthermore, the study of starbursts is crucial for understanding the evolution of galaxies in the local universe. Observing the different phases of star formation in nearby galaxies can provide valuable information about the ongoing processes that shape their evolution. This includes studying how different types of galaxies, from spiral galaxies to ellipticals, undergo starbursts at different times in their life cycles, and how these bursts of activity impact the overall dynamics of the galaxy. Another important aspect of starbursts is their relationship with galaxy mergers and interactions. Mergers between galaxies can trigger intense periods of star formation, as the gravitational interactions between the galaxies funnel gas and dust into the center of the merged system. This influx of material can fuel a starburst, which can then lead to the rapid formation of new stars. However, the consequences of such mergers are not always straightforward. While some mergers result in the formation of new star-forming galaxies, others lead to the creation of elliptical galaxies, which are characterized by older stellar populations and little to no ongoing star formation. These complex outcomes highlight the dynamic nature of galaxy evolution and the influence that external interactions have on the development of galaxies. As we move forward in our study of starbursts and their role in galactic evolution, one of the most important areas of research will be understanding the relationship between starbursts and supermassive black holes. The link between these two phenomena is still not fully understood, but it is clear that they are closely connected. During a starburst, the gas flowing into a galaxy can fuel the growth of a supermassive black hole at the center of the galaxy. In turn, the energy released by the black hole can have significant effects on the surrounding galaxy, regulating the rate of star formation and influencing the overall dynamics of the galaxy. This intricate relationship between starbursts and supermassive black holes may be one of the key factors that govern the evolution of galaxies over cosmic timescales. The intricate relationship between starbursts and supermassive black holes brings us closer to understanding the symbiotic dynamics that occur within galaxies. When galaxies experience starbursts, they often produce vast amounts of gas and dust, much of which is funneled towards the center of the galaxy due to gravitational forces. This gas can feed the supermassive black hole that resides there, causing the black hole to grow and become more active. In some cases, this process can lead to the formation of an active galactic nucleus, AGN, where the energy from the black hole, in the form of intense radiation and jets, can influence the surrounding galaxy and even trigger additional star formation or shut it down. As the supermassive black hole consumes the material, it generates powerful feedback that can have a lasting impact on the galaxy's evolution. This feedback mechanism can regulate the rate of star formation, not just by stripping away gas from the galaxy, but also by preventing further star formation through the energetic outflows created by the black hole. These outflows can inject heat and momentum into the surrounding gas, essentially blowing away the material needed for new stars to form. This feedback process, the feedback from supermassive black holes during starburst events, can also have large-scale effects on the intergalactic medium. These energetic events can heat the surrounding gas to millions of degrees, preventing it from cooling and collapsing to form new stars. Over time, this leads to the transformation of galaxies from star-forming systems to older, more passive galaxies, significantly altering their structure and the types of stars they host. The interplay between starbursts, supermassive black holes, and the surrounding gas is a major driver of the diverse range of galaxy types that we observe in the universe today. Moreover, the role of starbursts in the early universe is particularly intriguing when we consider the formation of massive galaxies. The process of starburst-driven feedback is believed to have been especially important in the early stages of the universe, during the so-called cosmic dawn, when the first galaxies were forming. During this period, galaxies were smaller and gas-rich, and the rate of star formation was much higher than it is in most galaxies today. Starbursts in these early galaxies would have been far more intense, potentially playing a significant role in the rapid growth of galaxies and the early enrichment of the intergalactic medium. By studying the remnants of these starbursts in high redshift galaxies, we can gain insight into the processes that led to the formation of the first massive galaxies, and how they influenced the larger-scale structure of the universe. In addition to the feedback mechanisms, starbursts are crucial for the chemical enrichment of the universe. Stars are the factories where elements like carbon, oxygen, and nitrogen are created through nuclear fusion. When these stars reach the end of their lives, they explode as supernovae, releasing these heavy elements into the surrounding space. In a starburst, the sheer volume of stars being formed increases the rate at which these elements are produced and expelled into the interstellar medium. Over time, this process leads to the gradual enrichment of the galaxy and the broader intergalactic medium. This ongoing cycle of star formation, stellar death, and chemical enrichment is fundamental to the evolution of galaxies and the universe as a whole. The heavy elements produced during starbursts also play a crucial role in the formation of planetary systems. The carbon, oxygen, and nitrogen that are scattered through the galaxy provide the essential building blocks for the formation of planets and, eventually, life. Without these elements, the conditions necessary for life as we know it would not exist. The process of star formation, therefore, not only shapes galaxies but also has profound implications for the potential for life elsewhere in the universe. Interestingly, starbursts can also reveal much about the life cycle of galaxies and their interactions with their environments. Galaxies are not isolated objects but are constantly interacting with their neighbors and the larger cosmic web. Starbursts often occur in galaxies that are undergoing some form of interaction, whether it be a merger, a close encounter with another galaxy, or the accretion of material from a nearby galaxy cluster. These interactions can trigger bursts of star formation by funneling gas towards the galaxy's center, initiating a new phase of activity. Understanding the dynamics of starbursts and interacting galaxies is essential for understanding the full picture of galactic evolution. The study of starbursts in different environments also provides important clues about the impact of galactic clusters and the large-scale structure of the universe. In galaxy clusters, galaxies are densely packed together, and interactions between galaxies are frequent. In these environments, starbursts can be triggered by the gravitational interactions between galaxies or by the intrusion of hot gas from the intracluster medium. These bursts of star formation in clusters can provide insight into how galaxies evolve in crowded environments, and how their interactions with their neighbors can influence their star formation history. Starbursts in these contexts might also help explain the presence of some of the most massive galaxies in the universe, which are often found in the densest parts of clusters. Beyond our local neighborhood, starbursts also play a significant role in the cosmic web, the vast network of interconnected galaxies and galaxy clusters that make up the large-scale structure of the universe. In the early universe, the most massive and energetic starbursts may have occurred in regions where galaxies were just beginning to form and interact with one another. These early bursts of star formation may have had a significant impact on the growth of the first galaxy clusters and the formation of the cosmic web. The study of distant, high-redshift galaxies that are undergoing starbursts can provide us with a glimpse into the conditions that existed during the infancy of the universe and how the large-scale structure evolved over time. As we continue to explore the role of starbursts in galactic evolution, astronomers are turning to more advanced observational techniques to study these energetic events in greater detail. Observatories that span a wide range of wavelengths, from optical to infrared and radio, allow scientists to observe starbursts at different stages of their development and in different environments. By combining observations from ground-based telescopes, such as the Atacama Large Millimeter Array, ALMA, with space-based telescopes like the Hubble Space Telescope and the James Webb Space Telescope, astronomers are able to study the conditions that give rise to starbursts and how these events shape galaxies over time. The discovery of massive starbursts in distant galaxies is a significant step forward in our understanding of the evolution of the universe. By studying the remnants of these starbursts, scientists can learn more about the formation of the first galaxies and the processes that led to the creation of the large-scale structures we observe today. The study of starbursts also provides insights into the future of our own galaxy, the Milky Way, which may experience its own burst of star formation in the distant future, possibly as a result of interactions with other galaxies in our local group. Looking ahead, the role of starbursts in galactic evolution will continue to be a major focus of research. As our observational capabilities improve and we gather more data on distant galaxies, we will be able to build a more complete picture of how these events shape the structure and evolution of galaxies. Starbursts not only illuminate the process of galaxy formation but also offer a window into the broader processes that govern the universe. Their impact is felt across cosmic timescales, influencing the formation of stars, the creation of heavy elements, and the evolution of galaxies. By understanding starbursts, we unlock one of the key pieces of the puzzle of galactic evolution, and with it, a deeper understanding of the universe itself. As our understanding of starbursts continues to grow, so too does the realization of their importance in shaping the broader cosmic landscape. One of the most fascinating aspects of starburst galaxies is their ability to undergo rapid transformation. In a short amount of time, these galaxies can go from being relatively normal to displaying intense star formation rates that dramatically alter their appearance and evolution. This rapid transformation challenges traditional ideas about how galaxies evolve and provides a unique insight into the processes that drive their growth and decline. The high rate of star formation during a starburst means that large amounts of gas are being converted into stars at an accelerated pace. This gas is typically composed of hydrogen, the most abundant element in the universe, and is often found in the form of molecular clouds. These clouds are dense, cold regions of space where stars are born. When a starburst occurs, these clouds are compressed and heated, causing them to collapse and trigger the formation of new stars. This burst of activity can lead to the creation of star clusters, some of which are among the youngest and most massive groups of stars in the universe. What makes starbursts particularly intriguing is the way they influence the surrounding environment. The intense radiation and winds produced by the newly formed stars can have a profound impact on the interstellar medium. In the most extreme cases, the outflows from these stars can blow away large portions of the gas in a galaxy, quenching further star formation and potentially even leading to the galaxy's eventual decline. This feedback loop, where star formation triggers the release of energy that then inhibits further star formation, is a key factor in the overall evolution of a galaxy. The rate at which gas is consumed in a starburst also has significant implications for the galaxy's future. In galaxies experiencing starbursts, the available gas supply may be depleted in a relatively short time, leaving the galaxy unable to sustain further high rates of star formation. This can lead to a shift in the galaxy's evolutionary path, from a star-forming system to a quiescent one. Over time, galaxies that have undergone multiple starbursts may find themselves with very little gas left, becoming passive, older galaxies that are no longer capable of producing new stars. Interestingly, some of the most massive galaxies in the universe are thought to have undergone a series of starbursts during their early history. These starbursts would have played a crucial role in the rapid growth of these galaxies, allowing them to accumulate large amounts of mass in a relatively short period of time. Over time, these galaxies may have merged with other galaxies or undergone other interactions that further shaped their evolution. The study of these massive galaxies and their starburst histories is crucial for understanding the processes that lead to the formation of the largest and most evolved galaxies in the universe. Starbursts also provide valuable insights into the role of dark matter in galactic evolution. Dark matter, which makes up a significant portion of the mass in the universe, is thought to play a critical role in the formation and structure of galaxies. In starburst galaxies, the distribution of dark matter may influence the rate of star formation and the overall evolution of the galaxy. For example, in galaxies with a large amount of dark matter, the gravitational influence of this invisible matter could help to retain gas and prevent it from being blown away by the powerful winds from newly formed stars. This could allow for longer periods of star formation and a more sustained starburst event. Conversely, in galaxies with less dark matter, the lack of gravitational support could make it easier for the gas to escape, leading to a quicker depletion of the galaxy's gas supply and a shorter-lived starburst. The study of starbursts also sheds light on the role of gas accretion and galaxy mergers in galactic evolution. Gas accretion, the process by which galaxies accumulate gas from their surroundings, is an important driver of star formation in many galaxies. During a starburst, gas is often funneled towards the center of the galaxy, where it is compressed and heated, triggering the formation of new stars. This gas may come from a variety of sources, including the intergalactic medium, neighboring galaxies, or the remnants of past starbursts. In some cases, gas accretion can trigger a new round of star formation, leading to another burst of activity. In other cases, a merger between two galaxies can provide the necessary gas for a starburst, as the gravitational forces of the collision compress the gas and trigger a new wave of star formation. Understanding the relationship between starbursts and galaxy mergers is particularly important for unraveling the history of galaxy formation. Many of the most massive galaxies in the universe are thought to have formed through a series of mergers, with each merger triggering a new round of star formation. These mergers can result in the formation of massive elliptical galaxies, which are characterized by their lack of ongoing star formation. The starbursts that occur during these mergers are thought to be responsible for the rapid growth of these galaxies, as they allow for the rapid accumulation of gas and the formation of large numbers of stars. Over time, however, the gas supply may be depleted, and the galaxy may transition to a more passive, quiescent state. The interplay between starbursts, galaxy mergers, and the evolution of the intergalactic medium is a fascinating area of research. As galaxies merge and interact with one another, the gas within them is redistributed, often triggering bursts of star formation. These interactions can also lead to the creation of large-scale structures in the universe, such as galaxy clusters and superclusters. The energetic feedback from starbursts can have a profound impact on the surrounding gas, heating it and preventing it from cooling and collapsing to form new stars. This feedback, combined with the complex dynamics of galaxy mergers, plays a crucial role in shaping the large-scale structure of the universe. As we look to the future, the study of starbursts and their role in galactic evolution will continue to be a central focus of astronomical research. New observational techniques and more powerful telescopes, such as the James Webb Space Telescope, will allow scientists to observe starbursts in greater detail and at earlier stages of the universe's history. By studying the remnants of starbursts in distant galaxies, we can learn more about the processes that shaped the formation of the first galaxies and how they evolved into the systems we observe today. The role of starbursts in the cosmic cycle of gas, stars, and elements will provide crucial insights into the fundamental workings of the universe. Starbursts are not just spectacular displays of stellar birth and death. They are fundamental drivers of galactic evolution. Through their intense bursts of star formation, they shape the structure, chemical composition, and future of galaxies. Whether triggered by internal processes, external interactions, or the influence of supermassive black holes, starbursts leave an indelible mark on the galaxies they inhabit. They contribute to the creation of the heavy elements that form planets and stars, regulate the rate of star formation, and play a central role in the growth and decline of galaxies. As we continue to study these cosmic fireworks, we gain a deeper understanding of how galaxies form, evolve, and ultimately reach the end of their life cycles. The study of starbursts is, therefore, not just about understanding a specific type of galaxy, it's about unraveling the mysteries of the universe itself. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.